right, sweet. Hey, good morning, guys. Welcome back. What was that? Okay. Hey, good morning. Welcome back. So here's what we've got for today, right? So we're gonna recap the oil prop and the hydraulic system today that we talked about yesterday, and then we're gonna go into the fuel and the electrical system. So four briefs for today. Gonna be a pretty long day. Normally Keith is here to help me. However, it's just gonna be me today. He's home sick right now. All right, so we're gonna go ahead and jump right into it. Okay. Cool. Starting with the oil prop system, going over the EP of the day, the question of the day, and the limit, right? So let's hit the question of the day and the limit real fast. The oil system capacity, right? Remember that's going to be 18.5 quarts, right? And the oil temperature for takeoff at max. Let's look at the limits page over here. All right, cool. So oil system for or oil temperature for takeoff at max, right? So we're gonna go all the way over to the temperature column. Takeoff at max, we're gonna be anywhere between 10 and 105, right? Remember that normal oil temperature range. It's where we should be in the green there. Um, for the question of the day, we have uncommanded power change, loss of power, and uncommanded prop feather, right? So all of this. First of all, let's talk about the CP, right? Um, so uncommanded power changes, right? This is all three EPs in one, really, because all of the action items are going to be the same, right? But uncommanded power changes is exactly what it sounds like, right? So we're looking at our torque gauge. So the torque gauge is going to be going up and down, and we're not going to be doing anything to the throttle, right? So that's your uncommanded power changes. Uncommanded or loss of power is going to be similar to that. We're just going to be losing power, slowly going to be going down as even though we're not pulling back on the PCL, right? And then for uncommanded prop feather, this one's going to be kind of different, right? Um, we're going to see torque actually go through the roof, right? So torque is going to go way up into the red line, but we're going to see our NP drop, right? So our propeller is feathering. We don't intend for it to. So that NP is going to go drop down, right, somewhere below 40%, and then torque is going to go through the roof because there's going to be less resistance, right, as that prop is feathering, and the engine's still going to be spinning it. So we're going to see that torque go way up. Um, so that's going to be the kind of difference in these three Ps. It's important to know what they look like, right, as you're studying them, because when you get an EP in the aircraft, right, be it real or simulated, it's not gonna tell you what exactly it is. So you need to know the indications or what it's gonna look like to you on the actual gauges there, right? So that's what this one's gonna kind of look like, right? Let's talk about more about what it is, right? So we're gonna go over to the PCL and drop down engine, uncommanded uncommanded power changes, loss of power, and uncommanded prop feather, echo 7. This echo delta. All right. So first of all, I remember when I was first learning this CP, right? It's got 9 steps you got to learn, and at first, I remember it being kind of one of the ones that was more of a pain in the ass because some of the other ones tend to be a little bit have more steps to them. However, once we talk about this and once you start to think about what these steps are, it tends to be one of the easier ones to remember, right? This is probably my favorite EP to go through. I don't know, just because it kind of makes sense to me, right? So the first thing we're going to do is PCL mid range, right? And we've got 3 notes associated with that. All right, so mid-range is a physical PCL angle that approximates the midway position between idle and max, right? So yeah, mid-range is somewhere in the middle, that Goldilocks position, right? A PCL position above idle will provide the best chance for the engine to recover, and the mid-range PCL position will minimize the potential for engine over torque and over temperature when the PCL is turned off, right? So not too high, not too low, directly in the middle is where we want it to be, right? Now I'm about to show you why that is, okay? Next thing we're going to do is PMU switch off, right? So remember that PMU is that power management unit. It's what's going to be controlling the power, like kind of like it's the computer that's in charge of controlling the power for the aircraft, right? Based on what you tell it, how fast you want to go with that left hand, right? We've got 2 cautions associated with that, right? So turning that PMU switch off. There's potential for ITT limits to be exceeded with when the PMU is switched to off with ITT greater than 820 degrees Celsius, right? So when you turn off that computer controlling of the aircraft power, right, you could see a rise in ITT. And if you're already too hot, right, then you could exceed the limits. Um, that's why PCL mid-range is important, right? And then ground idle will not be available during landing, rollout, and taxi. Plan for increased landing distances due to a higher idle in one, approximately 67%. Yeah, again, we're losing that kind of computer control, right? So normally when you get on the ground, it does check down to about 60, 61%. It's not going to do that with the PMU off. So that's that caution there. You're just going to be landing a little bit faster. Not super applicable for right now, but worth noting, right? But let's check this out, right? So PCL mid-range and PMU switch off, right? Let's talk about why that is. Coming over here to the um, this thing. All right, so over here we've got the this graph right here. So this graph is power distribution, right? It's basically, it says power distribution over time, but it's basically power in relation to PCL position, right? Um, So with the PMU on, we've got a nice linear response because we've got that computer control, we've got that governing happening automatically, right? It's very linear. As you increase a little bit on power, right? As you increase a little bit on PCL, you're going to get a little bit on power, right? And it happens very as you'd expect it to, right? With that PMU switch off, right, we kind of lose that linear governing of the power, and it tends to be again, we've got that mechanical governing. It's what's going to be doing it, and it tends to be a lot more exponential in nature, right? So that's why the first thing we want to do is PCL mid-range, because mid-range is going to be the spot on this graph where the two graphs most line up, right? So it's going to be where they cross right there. So PCL mid-range, if we're too low, I mean, it would drop down and be too low. If we're too high, then we could see that spike in ITT, or we could over torque or over temp the engine, right? So that's why we want to be right here in the middle before we turn that PMU switch off, so that we don't have much of a change with our power when we switch the PMU switch off, right? So that's why we're doing that on this graph here, right? So I'm just gonna get that back down to normal. Cool. All right, so that at least helps me remember the first two steps, because normally most of the EPs, the first step is like do something with a PCL, right? Well, in this case, this is the only one where PCL goes to mid-range, and that's the reason why, is because we're turning that PMU switch off, right? So that helps you remember things. Prop system circuit breaker on the left front console, right? Pull if NP is stable below 40%, right? So the first thing we got to do before we do this step is check our NP. Remember that NP is that tiny little box right at the very top between torque and oil pressure, right? So you're going to check your NP and see if it's stable below 40%. If it's stable, or if it is below 40%, then we're going to pull that prop system circuit breaker. Remember that prop system circuit breaker is the one that we just talked about. It's the one that you have to have memorized or be able to find blindfolded. So it's here on the left side, right? You go down three, find the gap, and then it's the one over here in the second row. So it's the one right next to the gap. That's your processing circuit breaker. And the reason you have to be able to find it blindfolded is because of the CP, right? Remember, what is the prop system circuit breaker is going to give power to the feather dump solenoid, right? And that's what's going to allow the oil to exit out of the pitch change mechanism, right? Well, if the NP is stable below 40%, then we don't want that oil to exit. We want that NP to go back up. We want our prop to come out of feather and go back to where we want it to be. So we've got 100% NP. In order to do that, we have to trap the oil in the pitch change mechanism. Now, we talked about two doors for the way that it exits, right? We've got the prop servo valve, and the prop servo valve gets a signal from the PMU, and the PMU is already off, right? So we don't have to worry about that one being the one that the oil is escaping out of. So now, if NP is still stable below 40% after turning off the PMU, we know it has to be the prop system circuit breaker, right? So we're going to pull that prop system circuit breaker. We're going to trap that oil in the pitch change mechanism, and hopefully we're going to see that we're going to get that oil pressure back in there. It's going to bring our prop out of feather and back into like normal conditions, right? So that's kind of the importance of that step on the CP here, right? Is prop system circuit breaker pull if NP is stable below 40%. Now we've got a few notes with that, right? So 6, 7, and 8. With constant airspeed and torque, RPM can be considered stable below 40% with no upward change for a 3-second period, right? So if you're stable at 40%, basically, yeah, it's not going up for 3 seconds. That's kind of what that defines stable. If NP indicator is displaying red X's, switching the PMU to norm and back off will reset the PMU and may restore the NP indication. So that's that's what that one could be. If you don't have an NP indicator and it's red X's, just switching the PMU off and back to norm could get it back, right? Typically, if something is not working on one of your displays, it'll just put a red X in there in place of it, right? And then the prop should come out of feather within 15 to 20 seconds, right? So as we close that feather dump solenoid, right, we're going to get that oil pressure building back up in, and that's going to move the prop out of feather and back to where we want it to be. So 15 to 20 seconds. It's kind of don't freak out if it's not happening immediately. It might take a little bit of time. All right, cool. So those are the first three steps, and then the next step is PCL is required, right? So PCL mid-range, props, PMU switch off, check my NP if NP is stable at 40%, and then props and circuit breaker pull, then PCL is required. We've got a warning and a note with this one, right? If rate of descent indicated on the VSI while stable at 125 knots with the gear flaps and speed brake retracted and 4 to 6% torque is greater than 1,500 feet per minute, right? So real fast. Whenever you are coming in to be a glider, right? So if you have to shut your engine off and fly PEL or force landing or whatever, you're going to go to your best glide condition, right? Best glide condition is going to be 125 knots clean, and then prop at 4 to 6%. Really, what that represents is it's a simulated glide condition, right? If you pull your prop back to 4 to 6%, basically the thrust from the prop equals the drag from the prop. So it's like a simulated glide condition, right? If you're at your best glide condition and your VSI is greater than 1,500 feet per minute, right? Um, at best glide, this should be the max rate of descent that we see, right? And that's even kind of on the high end, right? So what you're allowed to do is if you to achieve that best glide, increase the torque as necessary up to 131% to achieve approximately 1,350 to 1,500 feet per minute. That's the range that we're looking for. That's going to match our glide rate. For rate of descent. And then if engine power is insufficient to produce a rate of descent less than 1,500 feet per minute, set the PCL to off, right? So a couple of things here, right? How do we get 131%, right? Well, we're back on that exponential like side of the graph over here. So it doesn't really show it, but you can go above 100% with that PMU switch off, right? When they kind of stopped it, you see they went back down before they got to 100%. But you can go up to 131%. That's going to do a lot of damage to your engine, right? But if the engine is already kind of like choking on you, well, we're going to go ahead and use what we can get to arrest that VSI, right? So we can at least try and become a glider a little bit easier. So that's how you get up to 131%, and you want to get that into that range, 1,350 to 1,500 feet per minute for our best glide. If the engine power is insufficient so if we're insufficient to produce a rate of less than 1,500 feet per minute, then we're going to set that PCL to off. This is saying, hey, we're better with our engine off than we are with our engine on. And what could be causing that, right? If we are clean right now, right? So we're clean with no drag on the aircraft, and our biggest suspect is going to be that prop, right? Not coming out of feather, or not coming out of, or not being at where it needs to be, right? If our prop is causing more drag than it should be, right? If we're at 4 to 6%, it should be kind of like minimum drag condition, right? But if it's causing more drag than we need to, that's what's going to increase our VSI up to 1,500 feet per minute. If it's greater than that, we're just going to say, hey, screw the engine, we're better off as a glider, and we're going to set that PCL to off, right? And then the other note down here, the pilot should consider moving the PCL to the full range of motion to determine power available, right? All right, cool. So now, if power is sufficient for continued flight, right? Well, what does sufficient for continued flight mean, right? It means that we can achieve this rate up here, right? Something between 1,350 and 1,500 feet per minute on our VSI at 4 to 6% torque at 125 knots and clean. Okay, so if power is sufficient for continued flight, then we are going to execute a PEL, right? Which is we're going to turn towards the nearest airfield. We're going to set up for our ELP, that emergency landing pattern, and we're going to be able to fly that with the engine on. So if we've got the power sufficient for continued flight, we're going to execute a PEL. If power is insufficient to complete a PEL, insufficient basically means the opposite of that, right? We are clean and everything, and we still can't achieve a rate that's less than 1,500 feet per minute. We're going to say that's insufficient for continued flight. Then we are going to we're going to do the rest of this, right? So prop system circuit breaker reset as required, PCL off, firewall shut off, handle pull, and then execute force landing or eject, right? So eventually, where this is either going to be a force landing, which means we're flying that ELP without our engine. That's what we're doing when we turn our PCL off, or we're ejecting because we don't want to land with this plane, or we can't find airfield to land at. Okay. So, a couple of caution and a warning with this one. So, if power is insufficient to complete a PEL, we've got our caution up here. Consideration should be given to leaving the engine operating with PCL at mid-range, right? So, leaving that PCL at mid-range and leaving that engine on, right? If we've got the altitude to do it, even if we can't achieve a rate that's less than 1,500 feet per minute, but say we're up at like 20,000 feet or something, we've got plenty of altitude to burn, right? We're going to keep that engine. We could keep that engine going for a little bit, which is going to prolong everything else that's running on the plane, right? So all of your other, everything that's run off the accessory gearbox and all of your electrical components, right, could prolong the amount of time that you've got those by keeping the engine running, right? So that's something, a consideration you've got. Definitely, if you're at low altitude, probably want to get rid of that engine because you're about to come into land. So go ahead, shut it off, and execute a PEL. But if you've got a lot of altitude beneath you and a lot of time, it's a consideration. Prop system circuit breaker reset is required. So with that one, right? So this one's super important. If you pulled the prop system circuit breaker up here, and now you want to go to shut the engine off, right? Well, we want that prop to feather when we shut the engine off, right? But the prop's not going to feather with the PMU switch off and the prop system circuit breaker pulled, because that's essentially got both of our valves, the prop servo valve and the feather dump solenoid, are closed. So that feathering spring is going to have to push that oil somewhere. It can't go out like normally does. It would have to push it back through the system, right? Which means that with the prop system circuit breaker pulled and the PMU switch off, the feather dump solenoid will not be powered. The propeller will feather at a slower rate as oil pressure decreases and the feathering spring will take effect. Glide performance will be considerably reduced and may not be possible to intercept or fly the emergency landing pattern. So, without resetting that prop system circuit breaker before we shut our engine down, it's going to be really tough. That prop's not going to come out of feather. You're going to see a VSI way greater than 1,500 feet per minute, and it's going to be tough for you to be a glider. So reset that prop system circuit breaker, then you can shut everything down. So PCL off, firewall shut off, handle pull, and then execute that force landing or eject. So that's going to be the EP of the day right here. Again, like I said, that tends to be one of the ones that most people are kind of afraid of at the beginning, but just because it's got a lot of steps. But if you think about it and what those steps mean, then it should help you, right? Did someone ask a question? Oh, no, good, okay, cool. All right, cool. So that is the stuff at the beginning of the day. Let's go through the actual system itself as if you're a drop of oil in the oil system. And down here. All right, cool. So your drop of oil in the oil system, the first place you're going to be is you're going to put into the tank, right? Remember, you're not going to ever put oil in this tank. The maintainers are. They're going to be the ones who are checking the oil and doing everything, right? Remember, they're going to check the oil with a dipstick, and they're going to check it within 30 minutes after you shut down the engine, and they're going to service it between they're going to service it within 30 minutes, and they're going to check it between 15 and 20 minutes after engine shutdown for the most accurate results, right? So that's how they're going to check it, right? You go into this tank with 18.5 quarts of all your friends of other oil in here, right? And then you're going to get sucked up by the pump, right? So you get the engine-driven oil pumps. You get the forward and aft pumps, right? That are both located inside the oil tank. Remember, those are driven by the accessory gearbox back here. So you're going to get sucked up by the pumps. The pumps have two pickups. One is near the center of the tank, and one is near the top of the tank, right? The top of the tank is for inverted flight, so you can get more oil picked up as if you're upside down. Cool. So those pumps are going to send that oil up to the oil filter, right? Filters filter until they don't, they bypass, right? So we're going to get filtered, and if this thing becomes clogged, then it's still going to bypass. We're going to still, like, dirty oil is better than no oil, so we're going to still send that to places we need to go. Some of that oil is going to come off and go to the accessory gearbox, right? Accessory gearbox is going to be what drives a lot of the accessory components on the aircraft, right? So like your starter generator, your Hydes pump, your oil filter, your PMU, your fuel pump, and your fuel management unit, right? So all of this stuff is going to be driven by the accessory gearbox on the. It's kind of the back of the engine there. We'll show it to you when we get to the pre-flight. So that's the accessory gearbox, right? Remember, it's going to go and lubricate those bearings and those gears inside the AGV there. Then we're going to send the rest of the oil up to the oil temperature transducer and the oil pressure transducer. The temperature transducer is going to pick up temperature data. It's going to send that to the EDM, the engine data manager, and that's what's going to interpret that data and display it here on your ICAS display on your oil temperature gauge, right? And then we've got the oil pressure transducer. It's going to pick up that pressure data, send it to the EDM, right? Interprets it. But before it goes to the ICAS display, it's first got to go to the SCU, that signal conditioning unit. Remember that signal conditioning unit is there to filter out those nuisance signals, those nuisance warnings and cautions that could come on while you're flying, right? So that you don't constantly get oil pressure or cautions or warnings whenever you're maneuvering or doing aerobatics or something, right? So that SCU is going to filter out those nuisance signals and then send that to you, the pressure data on your to display on your pressure gauge right here. If you do get an oil pressure caution, right? Remember what the critical action item for this step, right? So we're going to terminate our maneuver, and then we're going to check our oil pressure. If oil pressure is in the green, then we're going to continue our operations. If we get the oil pressure caution for more than 5 seconds, or we get the oil pressure warning, or oil temperature out of limits, or oil pressure fluctuations, all that stuff, right? Then we are going to PCL, minimum necessary to intercept ELP, avoid necessary PCL movements, and then PEL execute, right? So we're going to set that PCL to a spot so that we're not jacking around our power, jacking around our oil too much. And then we're going to go ahead and fly that PEL before we get some kind of, if we have a problem with oil, right, we're having a problem with lubrication in the engine, then that could lead to an engine seizure. And that's going to be a worst case scenario, right? So we're going to do that precautionary emergency landing just in case we get that engine seizure, engine failure. So that's what we're going to get up here. Remember, if I ever get both the oil pressure caution and the oil pressure warning at the same time, and then I check my gauge and the gauge is in the green, that indicates an SCU failure. So worth noting there. All right, cool. Now the rest of that oil is going to come over to the gas generation section, right? We're going to go to lubricate and cool those compressor bearings. And then we're going to come over to the power turbine section. We're going to lubricate and cool those turbine bearings. And then we're going to send oil over to the reduction gearbox, right? We're going to lubricate those gears and those bearings and the RGB there, right? Remember, the purpose of the RGB is going to take that high speed, low torque on the engine side, approximately 30,000 RPMs, and convert it over to high torque, or so low speed, high torque on the prop side, right down to 2,000 RPM. So it's a 15-to-1 reduction ratio. And then we're going to go over to the PIU, right? Remember, the prop interface unit is what is going to send the oil down into the pitch change mechanism to move our prop, right? The PIU gets its signal from the PMU, right? Which you're going to do. You're going to tell the PMU how fast you want to go with your left hand on the PCL, right? So the PCL talks to the PMU talks to the PIU, and the PIU is going to say, all right, cool, he wants to go this fast. I'm going to put this much oil in the pitch change mechanism, right? Remember, that pitch change mechanism is it's a hollow cylinder inside the nose cone of the aircraft, right? It's got a piston and a spring inside there. As oil fills up that cylinder, it's going to push against that piston, push against that spring, and bring our props from feathered to low pitch blades, right? Remember, feathered blades are going to be, it's the no oil pressure condition or no engine condition, or like when the engine is shut off. Our blades are going to be feathered approximately 86 degrees from the perpendicular plane, and then we're going to put the maximum amount of oil in there and go all the way from feathered through high pitch blades and all the way down to low pitch blades, which is going to be the maximum oil condition, and that's going to rotate our blades to 15 degrees from the perpendicular plane. So those little thin slices, right? We've got low pitch blades for low speeds and low throttle settings, but it is the maximum oil condition, so it's kind of counterintuitive. And then anywhere in between low pitch and feather, that's going to be our high pitch blades or our coarse blades for you. Cool. Coming out of the pitch change mechanism, we've got two ways to get out. We've got the prop servo valve, right? The prop servo valve gets its signal from the PMU, right? So the PMU has to be operational for that thing to work. And then the other exit is the feather dump solenoid, right? That dump solenoid gets its signal from the prop system circuit breaker, right? We just talked about that at length. So both of those exits are going to be the way that the oil comes out of the pitch change mechanism when we shut our engine down, allowing our prop to go back to feather, right? Cool. So now, oil coming from the pitch change mechanism, the excess of the PIU, and the reduction gearbox, right, is going to first go through the chip detector down here. So it's all going to come through the same point. So the chip detector is a a little electric magnet with two prongs that stick out into the oil, and that's going to it's going to pick up any ferrous material, anything made of metal that's inside of our oil, right? As metal passes by it, it's going to get stuck to the magnet, right? If enough chips build up on that magnet and completes the gap between those two prongs, that's going to complete our circuit and give you a chip light, right? So that chip light right there is going to go off in your cockpit. Remember, the chip light has got it's the same critical action items as the last steps of oil pressure over here, right? So if you get a chip light, you're going to PCL minimum necessary to intercept ELP, avoid necessary PCL movements, and then PEL execute, right? So that's how the chip light's going to work there. And then all of the oil coming back is going to get sucked back through the scavenge pumps, right? I remember we do have pressurized delivery. Pressurized delivery up here is it's constantly squirting that oil and keeping these things drenched in oil, and then so that's how it gets there, and then we suck it back with our scavenge pumps, right? So we've got our external oil scavenge pumps and our internal oil scavenge pumps, right? Um, the internal oil scavenge pumps are actually inside the oil tank themselves, and again, they're driven by the AGV as well. They're going to suck back everything from the compressor section and from the accessory gearbox, and bring it back into the oil tank. If it's too hot, they're going to send it outside to go to the oil cooler and then back inside. And then everything coming back from the power turbine section and from the front of the aircraft is going to come back to the external oil scavenge pumps, right? Those external oil scavenge pumps, again, they are going to go through the oil cooler and then back to the tank. This is an air oil cooler, so what it's going to do is it's got cold air constantly blowing over it because it's at the front of the aircraft, just underneath the intake. So cold air is constantly blowing over this. As oil goes through it, that cold air cools it down, just kind of like blowing on your suit, right? Or the radiator in your car, and then it comes back into the tank. Cool. So that is your actual system going through. Let's go through our limits here real fast. So we've got our oil temperature limits. Remember, the lowest this could ever be is -40, but if it's ever -40 degrees Celsius in South Texas, you're going to have bigger problems than not being able to fly or share the T6. So -40 degrees Celsius, and then we go up to 10 degrees. That's going to be so -40 up to 105 is going to be our ground range, our limits there. And then for in flight, we've got 10 to 105, right? So those are that's our green range right there. Anything up here, 106 to 110, that's going to be our transient range, or ground ops less than 20% torque, right? We could see it at 106 to 110. That'd be like on a really hot day. But for transient, it's like whenever you're making a big move, you're going from like idle all the way to max, or you're doing some kind of aerobatics or something complicated. But once you go back to a steady state where you're just kind of straight and level for a second, then you should see things drop back down to 10 to 105. And then anything above 110 is going to be our warning area. That's going to be too hot for us, right? Usually means like the oil cooler is not doing its job for some reason, right? Or that you've got a clog somewhere in there that's preventing that. Um, Anyway, all right, so there's your oil temperature. Then we've got our oil pressure down here. So oil pressure, let's look at the bottom one first. So oil pressure for anything of greater than idle, right? We've got 0 to 40 is going to be that warning range, that red range. And then we've got 40 to 90, that's going to be our cautionary range, right? 90 to 120, that's going to be our green line, our green range. And anything above 200 psi is going to be our warning. And now that's going to be too much pressure where things are going to start popping seals and blowing valves and whatnot, right? And then the way to remember the bottom end is because pressure can't be anything less than 0 psi. So that's kind of how it's not the negative one. Up here we've got at idle. Everything remains the same except the lights change a little bit, right? So at idle, you got 0 to 15, you're going to get that warning range down here. 15 to 40, you're going to get that caution range, right? So it allows a little bit of a drop there, but the caution light will come on between 15 and 40. Or if it's greater than 5 seconds, then you'll get both the oil pressure and oil pressure caution and warning, right, for greater than 5 seconds. And then everything else remains the same up top. So that is the oil system. Are there any questions right now with the oil system before we move on to the Hydes system? It's kind of a fast review. We got 4 briefs to get through today, so just wanted to make sure we're good on time there. All right, cool. There are no questions. Let's jump over to the hydraulic system. All right. So the EP of the day is the landing gear malfunction. We'll get to that in just a second. But the pressure relief valve is going to activate at a range between something and something psi. That's going to be your 3250 to 3500 psi for the pressure relief valve. And then we've got our max airspeed for gear and flaps down, right? So this is going to be our max. Yeah, we're not going to want to exceed this with the gear or the flaps, right? That's going to be our 150 knots, right? That's going to be huge for you, especially when you're in the landing pattern, especially when you're doing PELs and stuff. You want to make sure that you stay below 150 knots, right? Now, let's go talk about our gear, our landing gear malfunction. Over here on the PCL. Oh, wait, I thought I didn't use it. Landing gear malfunction. Hydes, the first Echo Alpha up here. Hydes, landing gear malfunction. So it's literally the second EP, right? Echo Alpha 5. For this one, there's a lot to be talking about, right? First of all, with landing gear malfunction, you don't want the first time that you're going through the CP to be when you're actually having a landing gear malfunction in the aircraft. So let's talk about it here, right? It's not a critical action, or none of these are critical action items, but it is worth talking about. And it is a bit of a longer EP. It's kind of a two-pager there. Yeah. All right. So let's talk about the actual ones. The first thing we've got is landing gear malfunction. We've got 3 notes associated with it, right? So execute this checklist anytime landing gear does not indicate fully up with the gear handle up or fully down with the gear handle down, right? So we're looking for 3 green lights or no lights at all. Um, the aircraft is the preferred method of determining abnormal landing gear and inboard gear door positions. Time considerations permitting do not delay coordination for an aircraft visual inspection, right? So that is a huge thing here, right? If you've got a problem with your landing gear, there's always an IP on standby with the T6 who can just go grab it, hop up in the pattern, meet you in the pattern over the airfield, and then fly forms on you so he can get underneath you and check your landing gear just to verify that it's actually fully down, right? So that's always going to be an option for you is like here. As long as you've got time and conditions permitting, right? If you're all the way out at Goliad or if you're out on a cross country somewhere, maybe that's not going to be the case. But if you've got it available, especially in the local area, it's always available. Even like forms qualified IPs who are doing other flights up at different airfields, you can still have them come out and check it. As long as time and considerations permit, right? Remember, you are limited by fuel, right? So you want to get on the ground before you run out of fuel, but do not. So that's why you don't want to delay coordination for that. Um, if available, have another aircraft or RDO tower flyby report gear position visually prior to configuration change, right? So that's if you can't get another IP to join up on you, right? Any other aircraft, or if you do low approaches next to the RDO, maybe they can check your gear for you, right? Or fly by the tower. The tower's got some binoculars in there. They can look at the gear for you. But someone needs to check your gear, especially if you're unsure about your indications, right? Always use caution with that. Just it's better to have somebody check it and it be down than to land and have one of your landing gear collapse on you or something, right? All right, cool. So that is that. So if any safe gear down indications are obtained at any point, discontinue the checklist and land as soon as practical. Safe gear down indications are gear indications in both cockpits combined to show 3 green position lights regarding if gear warning tone or any combination of red position lights. As long as you've got 3 down and locked, right, and anywhere between the front cockpit and the rear cockpit, you're going to be good to go. Okay. So if he's got a nose and a right, and you've got a left and a nose or something, then all right, cool. That combines to make 3 down and locked. Okay. In that case, most of the time, it's usually just a light bulb that's been burnt out, right, in one of the cockpits. If either angle of attack indexer is illuminated, right, that's going to be a safe gear down indication. So up here, so this guy up here is our angle of attack indexer, right? He's going to come on only when your gear is down, right? Otherwise, when your gear is up, he's going to be turned off, right? And he's used. You're going to use some angle of attack approaches, in like I think it was late contacts or something like that. You do those angle of attack approaches where you're looking at it visually up here. It's only going to come down, or it's only going to turn on if your gear is down and locked, right? And like I said, here's what you're looking for indications down here. So 3 green down and locked on your landing gear indicators. So that's the first 2. Um, what's the next one? Landing and or taxi lights are switched on and illuminated, right? So with that one, landing and taxi lights only come on when your gear is actually down, right? You can't tell that from the cockpit, right? But who can tell that, right? It's going to be the RDO or anybody else who's checking your gear for you, right? So if they see both lights are on, that's going to be indication for you. Landing and taxi lights. So when you're all going to have to stand RDO at some point, right? Which is a runway duty officer. They put you in a box at the end of the runway. That's how they're. That's kind of your job. During the daytime, you're going to be responsible for checking the landing gear and making sure everybody's got their gear down before they come in and land. If not, you're going to hit the wave off lights. You're going to hop on the radio and tell them to wave off, right? If uh if it is nighttime though, that is your only indication, right? Because you can't see their gear, but if you can see two lights on the T6s, that means that their gear is down and locked, right? But do be careful. We've got the T44s that land out here too. They only have one. It's like a combined landing and taxi light on the nose gear. So it's only one light. So don't try and wave off a T44 that's coming in if it's for being a T6 with down gear or not down gear or something, right? T6 has two lights, landing and taxi light, and the T44s have the one light. If the main gear indicate down and locked and the inboard gear doors are fully closed, no red lights, the nose gear can be assumed to be down and locked, right? So, uh, yeah, so with this one, right, looking at our indications, actually Hydes system. I'm gonna show you this real fast, just because it's a little confusing the way they word it. Um, So for this one, right, you're going to get green lights and red lights, right? So green is down and locked, right? And then red is gears and transition, right? So the way that this works, just because the sequencing of the timing of the gear and the doors, if you got green down and locked here, and then the red lights go out on the main gear doors, right? Even though you still don't have a green light up here, then you can assume that it's down and locked just because of sequencing, right? Basically, if you get so remember the doors are going to open, right? Then the gear is going to come down, then the main or the nose gear is going to come down, and then the doors are going to close, right? The doors will not close if the main gear or sorry, if the nose gear is not down, right? So the doors will not close if the nose gear is not down. That's what that EP or that's what that note basically means there, right? Says if you get this one, these two red lights go out, so I've got two green on the main gear and I have no green on the nose light. Just the fact that those red lights went out and those doors closed means that you do have your nose gear is down. That's what that's saying right there. There's a note associated with that one. If only the nose gear indicates unsafe with the main gear down and locked and the inboard gear doors closed, no red lights. The nose gear down lock micro switch might be faulty. Pulling and resetting the landing gear control circuit breaker on the left front console may allow the hydraulic selector valve to center, causing the nose gear down lock micro switch to finish the sequence and provide a safe cockpit gear indication. So that's what that means. All right, cool. So if any of those are the case, you've got safe gear, you can go ahead and land, right? If you still don't have safe gear down indications, so you have none of this stuff, right? First thing you're going to do is you're going to remain airspeed remain below 150 knots so we don't overspeed our gear, right? Um, Gear handle down, press down firmly. If unable to lower the gear handle, execute the landing gear emergency extension checklist both, right? So anytime this checklist directs you to another checklist, immediately go to that one, right? So if you can't get that handle to go down, then you're going to go to the different one, right? Because that's the only way to get the gear down, or that's the other way to get the gear down. That landing gear, it's got a little pin inside of it. That pin is basically just going to be there to uh, it keeps the handle in place when the handle's up, but if it doesn't come out of the way, it usually comes out of the way just easily, right? As soon as you start to push the hand down, it doesn't take any pressure at all. But for some reason it gets stuck, then yeah, that's going to be preventing you from getting your gear handle down. Next thing we're going to do is we're going to do our lamp test switch, right? We're going to check 5 and 6 notes. From all landing gear position lights illuminate. All lights in respective cockpits will illuminate regardless of gear position unless the position light is burned out. Then the lamp test will not illuminate the gear position lights or the landing gear lights when the landing gear control circuit breaker is tripped, right? So with that, you do have a in the cockpit, you've got this guy. So underneath your PCL, you've got basically the system test panel down here. You've got the lamp test switch, which is this one there. When you hit that lamp test switch, all it's going to do is it's going to turn on everything inside the cockpit that has a light bulb, right? So all your indications and stuff. It turns those on so that you can determine if your light bulbs are burnt out or not, right? So that's what that was about. If you Yeah. So you want to confirm that you've got all your lights there, right? And then the note was with that circuit breaker tripped, then the lights aren't going to come on at all because that's what's providing the power to the lights themselves. All right, hydraulic pressure. Check if hydraulic pressure is below 1800 psi. Execute the landing gear emergency extension checklist. Continue this checklist if the hydraulic pressure is above 1800 psi, right? Remember, 1800 psi, if we've got anything less than that, our gear's not going to come down anyway. So you're going to check the hydraulic pressure. If it's less than, all right, cool. We know we're going to have to go to the emergency side. But if we still got above 1800, we're going to stay on this checklist until we don't have 1800 anymore. All right, landing gear control, that's going to be the circuit breaker on the left front console, the instruments on the left front console, and the instrument lights on the left rear console, right? Circuit breakers, check and reset. If unable to reset the landing gear control circuit breaker, execute the emergency extension checklist, right? So landing gear control circuit breaker. So if that circuit breaker or something in there is faulty and it keeps popping, right? That is going to be like the components that say, hey, put my landing gear down. But if that circuit breaker's popped, your handle's not going to work. It's not going to talk to the actuators and the solenoids and stuff. So if that is, then you have to go to the emergency side. We've got a caution and 3 notes. All right, so any electrical failure which causes the landing gear control circuit breaker on the left front console to trip will cause the position indicator lights and the lights in the gear handle to be inoperative. Additionally, a tripped landing gear control circuit breaker will cause the landing light, taxi light, and angle of attack indexers to be inoperative as well. So everything that tells us that our gear is down, at least inside the cockpit, is not going to be working without that circuit breaker working, right? This will leave aircrew unable to ascertain down and lock gear through internal indication, right? Any electrical failure which causes landing gear control circuit breaker on the left front console to trip will cause the landing light, taxi light, and angle of attack indexers to be inoperative. Any electrical failure which causes the instrument circuit breaker on the left front console in either cockpit to trip will cause the position indicator lights and the light and the gear handle to be inoperative in the respective cockpit. I feel like that basically said the exact same thing. So again, that landing gear control circuit breaker gives you all your indications, right? All right, cool. So that is, oh, and we've got a 9 note and a 10 note down here. So a tripped landing gear control circuit breaker on the left front console will cause the wait on wheel switch to revert to in-air functionality. This will result in a loss of ground idle RPM and result in longer landing rollouts, as well as the loss of nose wheel steering functionality. So again, that landing gear control circuit breaker means a lot to us for getting our gear down and landing. And then finally, 10 down here. In these procedures, the term reset is used to describe the action of resetting a circuit breaker that is already open. The pilot should assess the severity of the emergency and the equipment loss prior to resetting any open circuit breaker. Yeah, circuit breakers are there to they pop because something is getting too much power, right? If you're resetting it constantly, or you never want to do this, but if you ever press and hold the circuit breaker in, you're probably going to fry that piece of equipment because it's getting too many amps, and that's what's going to try and fry it. So only do it if you need to, and only do it if necessary, right? You're going to see that same note pop up anytime a circuit breaker is ever mentioned in the VCL. All right, so that was step 5 and all of the notes associated with it. Let's drop down here to step 6. All right, gear handle cycle. 11 in. Multiple gear handle cycles are permissible to achieve a safe landing gear configuration until critical fuel state is reached, and the pilot in command concludes that the continued attempts to cycle the landing gear risk more serious damage to the gear or loss of hydraulic pressure. So with that one, yeah, you can put it up and put it down as many times as you need to try and get it. It's like, it almost happened, but we're gonna try it again. You can do that as many times as you need to get that gear in a safe condition, right? Following actions while cycling or attempting to cycle the landing gear may result in successful landing gear extension, right? So applying symmetric G forces between 0 and 2.5 Gs with airspeed between 140 and 150 knots required to generate 2.5 Gs, right? So if you can apply some symmetric Gs, maybe things just aren't getting down and locked, right? Or maybe there's like, I don't know, some dirt in there that's preventing it from coming all the way down. If you can get it all the way down by applying those Gs, sweet, that's going to help us out. Applying side loads by slipping the aircraft, right? Maybe one's down and not the other, but we can slip it and try and get some air coming on that main gear or whatever to try and get it to come down and lock in place. Slowing your airspeed in no case should aircraft be slow below 90 knots or stick shift or whichever is higher, right? So this is again, it's just giving you more options, right? So if you slow down, maybe that will help things get down and locked, right? Actuating the speed brake or selecting flaps landing, both of those are going to create some turbulence and some dirty air underneath the plane. Yeah, maybe that'll help it get it down. Or making quick side to side movements of the gear handle in the front cockpit, right? So trying to get that gear handle down. Check the so all of those are going to be good tools for you to like kind of troubleshoot inside the plane. You've got options to do things with. Uh, Gear and gear door positions. Check if unable to check externally with another aircraft or RDO tower flyby, execute the landing with unsafe gear indications checklist. Right. So you want to have those positions checked, right? But if no one outside the plane is able to check it for you, then you're going to go to that landing with unsafe gear. You're going to assume it's unsafe gear until you land, and hopefully they're down. If not, then at least you're prepared to land with unsafe gear. If any of the following conditions remain, execute step 8, right? So both inboard main gear doors are partially open, right? Both inboard main gear doors are open with one or both main landing gear fully retracted. So the door is open, but one of the gears is retracted. That kind of sucked. Only one inboard main gear door is open. Only the nose gear is down and locked. Uh, a suspect a suspected landing gear jam caused by an external event, i.e., like a bird strike, a deer strike, or a hard landing, right? So if your gear is jammed, then we're going to land with unsafe gear indications or checklist executes. We're going to go to that checklist. If none of the preceding conditions exist, then we're going to go to landing gear emergency extension checklist executes. We're going to go to all those. So again, this is a longer EP, but it kind of gets you thinking about like, hey, what are some tools that I have at my disposal? How does my landing gear actually work, right? We know that landing gear circuit breaker's got a landing gear control circuit breaker's got a lot of authority in this process, right? But this also gives you some of the other indications, right, for how I know I've got good gear, and it also gives you some tools to try and get that gear down if necessary, right? Otherwise, any of these indications, then you go to another checklist, right? This will, I guarantee it, it will show up as the EP of the day multiple times while you are flying. So, oh wait, someone asked a question. Um, what is the expectation for the ones that need to be memorized, and which ones can be referenced for primary? Um, okay, so the ones that need to be memorized are all of the ones that are on um, the EP limits quiz, right? So the expectation here is that you know um, all of the critical action items and the notes, warnings, and cautions, right? The critical action items have to be verbatim. The notes, warnings, and cautions as close to verbatim as you can, right? Um, it depends on what squadron you go to, but it's worth starting to know. And like I said, the notes, warnings, and cautions are going to help you to understand things a little bit better for the critical action items. But yeah, for the ones that are that are on here, yes, you need to know those, right? For everything else, then the expectation is that hey, you're familiar with it, right? When it comes time to brief it, if it ever becomes the EP of the day, make sure you are of it competently with knowledge, not necessarily memorized. It looks better if you do it memorized. Just kind of depends on your instructor. Um, but yeah, that's what you should kind of be prepared for, right? I guarantee you, landing gear malfunction will be one of your EPs of the day multiple times through here. So be able to talk about that one with some good confidence, right? Especially because like this is the first time most people have flown a complex or like retractable gear aircraft. So that's worth doing it. I hope that answered your question. All right, cool. Man, you asked that like 15 minutes ago. My bad. All right. So let's go into the actual hydraulic system, right? Uh, we're going to brief it as if we are a drop of hydraulic fluid in the Hyde system. Put it at the top. All right, so drop of fluid in the Hyde system, right? So you are going to go into the reservoir. That's where you're going to be put initially, right? You're going to be in there with 5 quarts of your buddies in there, right? And you're going to be somewhere less than 50 psi inside the reservoir, right? Then we're going to get sucked up by the Hyde's pump. First thing we're going to go through is that firewall shut off valve, right? So that's going to be what cuts the Hydes fluid from going after the firewall before we get coming out of the engine-driven pump, right? Engine-driven pump is what's going to pressurize that hydraulic fluid up to 3,000 plus or minus 120 psi, right? Remember, then we're going to come out of the pump and go through a one-way check valve, right? Because pumps do not like reverse flow. Going through that one-way check valve, then we're going to go through a filter, right? Filters filter until they don't, they bypass, right? So this is going to be filtering our oil until it gets clogged, and then it's still going to bypass because dirty fluid is better than no fluid.
Yeah, we wrote. Sorry to interrupt you, but before you got too far ahead, I dropped a question in there.
Yeah. Yeah, so the uncommanded power change EP appears to look different than ATOPS. I look in the wrong place. What's up, buddy? Yeah, if you can get it to work. Yeah. You can try that one, see if it works. You got to plug it into the laptop station there. All right, so for this one, in the NATOPS, I don't know what you're talking about. For the actual let's go look at it real fast.
It's on page 2.
So the critical atoms are different than these.
It's on page 240. It's different than what's in the PCL. Like you're referencing the PCL, and then the NATOP like slightly different. So I'm just curious. Maybe I'm looking at it wrong or something.
Let's look at it real fast.
It's on PowerPoint 240 though.
NATOPS page 240.
Yeah. I said PowerPoint.
Am I in the right place?
Yeah, that should be it. Like, it should be either right above or below that diagram. No, down.
Down.
Yeah, that's not it right there. Nope, go down. Keep going down past that. There's like a big diagram.
All right.
Nah, you're past it. There's like it's literally, it is on page 240. I'm looking at it.
All right. Up here, 240.
Yeah. So the diagram that you just, okay, wait, stop. Okay. See where, right there. If experiencing uncommanded power, blah, blah, blah. And then it's like 1, zoom glide, and then blah, blah, blah.
Yeah, so that's a different EP. That's going to be up here. That's your engine failure. Yeah, so this is in flight. That's engine failure during flight emergency.
Okay, so how you tell them what EP it is, it'll be in bold like that. And then way down is the actual EP.
Yeah, well, so the NATOPS itself is going to give you all of the expanding information, right? So that's what all these graphs and stuff are here for. So this is going to tell you everything that you need to know about. So like there's a couple of notes in here and exactly what to expect when you get the engine failure in flight, like EP, right? So all this stuff, and then it's going to tell you, it gives you these graphs and everything to kind of reference as you're talking about it. And then it gives you the actual EP. So like, then you're going to zoom glide, right? So this is going to be these ones down here. So that's going to be the actual steps for engine failure in flight.
Okay, thank you for clarifying that.
Yeah. So does that make sense? So that's yeah, but that wasn't uncommanded power changes. That was engine failure in flight. So the one that we looked at is still the same. Cool. All right. All right. So back to the hydraulic system. So coming on back up here. All right. So hydraulic systems, we just got the hydraulic pump, right? That's going to pressurize us up to 3,000 plus or minus 120 psi. Then we're going to go through that one-way check valve because pumps don't like reverse flow. Next, we're going to go through is the filter, right? We talked about the filter. Filters filter until they don't, they bypass because dirty fluid's better than no fluid, right? Then we're going to come to the pressure transmitter. The pressure transmitter is going to pick up on that pressure, right? Pressure data from the fluid, and then send that over to the ICAS display and display it on your Hydes pressure gauge over there, right? Remember, we are going to get that check engine light if we get pressure less than 1,800 psi, right? So it tells us check engine if pressure is less than 1,800 psi. But we also get the check engine light if pressure is greater than 3,500 psi because you never have a hydraulic pressure low It's always check engine for above or below because it could be one or the other, right? Um, Cool. So that comes from the pressure transmitter. Next thing we're going to go through is our 3,500 psi relief valve. So that pressure relief valve right there is going to uh, determine if we do have too much pressure coming out of there. What it's going to do is open up and allow some of that pressure and some of that fluid to vent back to the reservoir, right? And that's going to hit the pressure reduction piston. It's going to drop it from that 3,000 or whatever it is greater than 3,000 back to less than 50 psi in an attempt to reduce that pressure. If not, say there's too much fluid on board, then we're going to go over the overboard relief valve and vent off some of that fluid just underneath the plane. We do get a high fluid low caution if we get less than 1 quart remaining in the system. Remember, there's a total of 5 quarts in the system, but if there's ever less than 1 quart, we will get that high fluid low caution there. Cool. The next thing we're going to hit is the slide valve assembly, right? Remember, the slide valve assembly is going to come into play whenever we switch to the emergency side, right? It's going to get pushed into place, and that's what's going to cut off the power package from the rest of the system so that the emergency side doesn't have to fight with the main side in order to put the gear down, right? So that's where that slide valve assembly comes into play right there. And then once it does, then the power package just becomes its own little small loop up here. The power package, separate from the power package and separate from the selector manifold, is going to be our nose wheel steering actuator, right? So it does get tapped off from the power package, right? And come down to move the nose wheel steering, right? That's because it doesn't necessarily take 1,800 psi to operate the nose wheel steering, and it's kind of like a nice to have component. So if you don't have the nose wheel steering, that's fine. But if the pump is still producing power, then we can still have, or still producing some kind of pressure. We can still have nose wheel steering even if we have gone to the emergency side if there's any pressure available up here. That's the way that does work. This fluid does end up getting filtered. But when we come down to the nose wheel steering actuator section down here, we've got a selector valve and we've got the actuator, right? So the selector valve tells the fluid which way to go on the actuator, and the actuator itself is going to be like a piston with a metal rod. It's going to be connected to whatever component. In this case, the nose wheel, and what it's going to do is it's going to push or pull to make that nose wheel go one way or the other. That's the same way that the actuators work for everything else down here. And the way that it pushes or pulls is going to be based on where the selector valve tells that fluid to go. So that's how that's going to work there, right? If you do turn the nose wheel steering on, right, remember you're going to do that with your either your ring finger or your pinky finger on the stick, right? You're going to get an NWS on, just a right there to let you know that it's actually on. And you're going to get that, what it's going to do is it's going to allow you to move your wheel just with your rudder pedals, plus or minus 12 degrees from center line. So that's how that's going to work for you there. Moving on down. Is it not working for you? Yeah. Try and go over to the wing. They've got a computer lab over there. If that guy's not working, I think it's easier. Those are better maintained computers anyway. Yeah. All right, cool. Hey, congrats on your wing, bro. All right, cool. So coming down to the selector manifold down here. So for the selector manifold, we've got the gear, right? Remember, the gear is going to be the one that's connected to 3 boxes here. So we've got the gear selector valves connected to 3 actuators for the left hand nose gear and right hand main gears. So that's going to be that, and it's also the ones that are connected to the emergency side as well. Moving on down, we've got our door selector valves. So that's going to be our inboard doors, right? Remember, the inboard doors have to come down and they come up just because of sequencing of the gear. So that's how that actuator is going to work there. Remember, it's going to be the one that also is connected to the emergency side, and it's right next to the one with the gear. Moving on down, the speed brake. So you've got your speed brake selector valve. It's going to be the one that's kind of all on its own over here. When you drop that speed brake, you will get the SPD BRK light out, right? Let you know that your speed brake is actually extended, and you're going to feel it inside the plane, right? It's going to feel like you're driving down a dirt road. That speed brake doesn't have a speed limit. You can use it whenever you need to, right? But recommend getting it in before you overspeed the aircraft at 316 knots, right? All right, dropping down to the flaps, right? So the flaps are going to be the only one with they have both a selector valve or 2 selector valves, one for flaps takeoff and one for flaps landing, going to the single actuator because it's only one rod that's going to connect to your flaps that are going to deflect it, right? Takeoff flaps are going to deflect down to 23 degrees, right? And then landing flaps are going to deflect all the way down to 50 degrees. So that's worth knowing there. All right, cool. So that's everything on the selector manifold on the main side over here. Then we're going to send fluid over to the through the hydraulic fuse, right? The hydraulic fuse is what's going to be what detects a leak in either side of the system and will close to prevent one side or the other system from losing all the fluid, right? If it leaks on the emergency side or if it leaks on the main side, the hydraulic fuse will close, hopefully saving one of these sides, right? Remember, it's going to detect the leak if it's greater than 0.25 gallons per minute with a max loss of half a quart, right? So that's what the numbers associated with that. Then we're going to go through a one-way check valve. Once the main side sends fluid to the hydraulic side, it stays on that hydraulic side and it stays at that pressure until we need it or we shut down the plane, right? It's going to send that fluid straight up to the emergency accumulator. The emergency accumulator is going to be like a kind of like its own reservoir that's going to keep that fluid in there, right? But the way that it maintains its pressure is that fluid goes in and compresses a helium precharge, right? So it compresses all that helium gas up to 3,000 psi, right? So that when it comes time and you pull that emergency landing gear handle, you're essentially going to release that helium is going to expand at 3,000 psi and push that fluid down to release your gear or to put down your gear or your flaps, right? So that's how that's going to work in there. Remember that the reason we use the helium up here is not because it's lighter than air. It's because it's an inert gas, which is going to be non-reactive with anything else, right? So that helium precharge, yeah, so that's going to be up there, providing all the pressure. Again, it's going to pressurize the same side. So the one pump that's pumping everything is going to put this thing over here. It's also going to be 3,000 plus or minus 120 psi. Next thing we're going to come to is the manual pressure release handle, right? This is what's going to be located in that hydraulic bay in the on the right side of the plane, just behind the trailing edge, the right wing. That manual pressure release handle, that's what's going to, whenever you land or whatever, you pull that handle, and that's what's going to release that pressure and that fluid to go back to the main side, and it goes back to the reservoir over here. And then we're going to go to the 3,000 psi relief valve. Does the same thing over here because we're going through a one-way check valve. So if this thing is fucked up and producing greater than 3,000 psi or 3,500 psi, then so will this side. It still needs to relieve that pressure. So 3,500 psi relief valve is going to send anything too high a pressure again back to the main side, so it can go to the reservoir or overboard to release that pressure. All right, cool. Coming on down here, we've got the landing gear emergency extension selector valve, right? That's going to be actuated when you pull the emergency landing gear extension handle, right? That's basically going to release all the pressure from the emergency accumulator and come down to the emergency side. Remember, it is going to come out. It's going to push that slide valve. It's going to push that slide valve in the way, which is going to block off the power package so that we're not competing with the main side. And then it's going to send that pressure and that fluid or high pressure fluid over to the main gear, right? Which is going to put down the main gear. It just goes directly to the actuators and puts your gear down, right? It's going to put your inboard gear down or inboard doors down too. Cool. Any pressure that's left over is going to come down here to the the flap emergency extension selector solenoid, right? So you're going to have your flaps that are going to be available to you, and that's going to send it over to the flap actuator. You can either put them at takeoff or landing, or you can go takeoff and then landing. But remember, if you go landing, you can't come back up to takeoff, right? It's one-time use kind of a thing because we're just using what pressure is left over here, right? Most of that pressure is going to go to put your gear down, right? If there is not enough pressure left for your flaps, tough luck. You can do no flap landing, right? The best way you can check that is you've got your E-hide pressure low, right? So you know that this is going to come on exactly halfway between a usable system and an unusable system between 3,000 and 1,800. It's going to come on at 2,400 plus or minus 150, and you get that E-hide pressure low. That is the hydraulic system. So that's everything on there. Are there any more questions right now? I'm going to take a quick break because I've been talking for an hour straight. So I'm going to take a quick break, go grab some water, and then we'll come back. We're going to do the fuel system and the electrical system. So that's what we're going to look for there. All right, I'll be right back. All right, we're about to get started in a second. All right. Let's do it, guys. All right, so two more briefs to go for today. We're gonna talk about the electrical system and the fuel system. Let's go with the fuel system first. That's what I'm gonna do. Normally, Keith is here and is able to help me out, so it's not so many briefs in a row. Uh, he does fuel and Hydes, and then I do electrical and or oil, but it's okay. He's puking his brains out, and we hope he doesn't have the Rona. So I got it. It's fine because I like PG. All right, the fuel system. Let's do this. Low fuel pressure EP. We're gonna talk about that here in a second. Max fuel for single point refueling. Anybody know that off the top of their head? It's going to be 1,100 pounds, right? So that is typically what you're gonna have, like pretty much a max, like 1,100 pounds of fuel. It sounds like a lot, right? Like that's a lot of fuel. It's really not that much, especially when you start thinking about like, I don't know, like the C-130 has like 35,000 pounds of fuel, something like that, and I don't know. Anyway, not a lot of fuel in this aircraft. We're about limited to at max about 2 hours of flight time typically. Max inverted flight time, we just talked about that. That is going to be 60 seconds. Let's talk about the low fuel pressure EP. Going over to the PCL and over here. All right, fuel. Where's it at? Is it an engine or is it its own? All right, low fuel pressure EP. Echo Charlie 3. Bravo. And Charlie. 1, 2, 3. All right. Low fuel pressure EP. Brutally simple. This is another one that's got critical action items, right? Um, First thing you're going to do is PEL execute. We've got a note associated with that. If the fuel pressure warning remains eliminated, the engine-driven high pressure fuel pump is suction feeding. Engine operation when high pressure pump suction feeding is limited to 10 hours, right? And then boost pump switch on. We've got a caution associated with that. Unless greater emergency exists, do not reset boost pump circuit breaker on the left front console if open. All right, so let's talk about the CP real fast. Low fuel pressure. What's that going to look like to you? You're going to get a fuel PX warning that's going to pop up on your ICAS display, right? That means you've got low fuel pressure, right? All right, cool. The first thing we're going to do is PEL execute turn climb clean, right? Right. So if we have the low fuel pressure EP, we've got two fuel pumps in this aircraft. We've got an engine-driven low pressure fuel pump and an engine-driven high pressure fuel pump. Right. If we have a low fuel pressure EP, that means that the low pressure fuel pump is not providing the high pressure fuel pump with fuel, which means the high pressure fuel pump is suction feeding, it's sucking that fuel straight from the tank. Right. It's not great for it. Right. So you can only operate with the high pressure fuel pump suction feeding for 10 hours. 10 hours. How is that possible if we've only got about 2 hours worth of fuel on this aircraft, right? Well, it's over the lifetime of the part, right? And when we go over next week to do the pre-flight in the aircraft, we're going to show you like the engines or the aircraft discrepancy binder, basically where they keep track of all that information. So for the amount of time that the engine-driven high-pressure fuel pump is suction feeding, they're going to keep track of it until it gets to 10 hours. Once it gets to 10 hours, then they're going to replace that part. That's how that works. Okay, so that's the first one, right? And then boost pump switch on, right? And then the caution over here is just talking about the circuit breakers, right? If the circuit breaker's already popped for the boost pump, then don't worry about it, right? The boost pump is what's going to be our third pump in the system. It's kind of a backup to the low pressure fuel pump. So if the low pressure fuel pump isn't working, the boost pump can operate kind of as a low pressure fuel pump and provide that fuel to the high pressure fuel pump. Now, let's talk a little bit about the way that this is written, right? So PEL execute first and then boost pump switch on, right? This is not saying, hey, I'm going to go ahead and fly a PEL all the way to landing and then hit that boost pump switch, right? Doesn't make any sense, right? This just means I'm going to go ahead and start my turn in the direction of the nearest airfield, getting set up for my PEL. And while I'm doing that turn, I'm going to hit that boost pump switch to on, right? The reason this is written the way that it is written, right, is to emphasize that the PEL is the most important thing you have to do, right? Now, why is our PEL the most important thing, right? If we've got low fuel pressure, we still have fuel, right? That engine-driven high-pressure fuel pump is still going to be working to provide fuel to the engine. Okay, it's not great for the pump, but it will be working because it's a pretty robust little part. It's a champion over there. But inside the engine, right? Let's see if I have a good picture of it. This is worth talking about because I think it's important. I've got it in the oil prop brief. Inside the engine compartment right here. All right, so let's look at this picture real fast. Go away. I can't show you because the little block is in the way. All right, let's do this. Up here, this thing, make it really big for us. Maybe. All right, so you can hardly kind of see it, right? But down here, so we're looking inside the left side engine compartment. This is my hydraulic pump, right? This is the accessory gearbox that runs all of these like components back here. And then down here, I've got my engine driven as the external oil scavenge pump, right? And it's driven on the same shaft as the engine-driven low-pressure fuel pump. So just believe me, there's a pump right here, and there's a pump right here on the engine, right? So the fuel pump is driven through the oil pump, right? Now, if I'm getting low oil pressure, my engine-driven low-pressure fuel pump is not working, right? If that low-pressure fuel pump is not working, then I can also assume that my external oil scavenge pump is not working as well. Well, if we've got problems with the oil system, right? If we've got oil that's not being circulated through the system appropriately, then what can we expect? Probably an imminent engine seizure. So the reason that the step is written the way that it is, PEL execute first, is because we're not anticipating a fuel problem. We're anticipating an oil problem, right? And if that oil problem is messed up, then we could get an engine seizure. So PEL first, and then while you're PELing, you're going to get that boost pumps or that boost pump and turn it on, right? So that's how that's going to work. Just why it's written the way that it's written on there, right? So anyway, that is your EP of the day. I don't know. I think that's a super important point. It's one of those ones that instructors like to be like, yo, does he know this or not? Oh, wait. Here we go. All right, cool. Yeah, all right, so I'm in the right spot. All right, let's talk about the fuel system. Jumping on down. Objective. We're gonna talk about the fuel system. Cool. Here's a fuel system, right? Fuel system here is brutally simple, right? It works exactly the way that you would think it works, right? We're moving liquid fuel from the tanks up to the engine. That's all that the system does. There are a couple of things in here that make it a little bit more complex than a typical fuel system, and we're going to talk about that. But you take all this complex stuff away, specifically the mode of flow, all those blue lines around there, then it works super simply, right? And that's mostly for straight and level flight. The mode of flow is going to help us out when we're doing aerobatics and doing cool shit, right? But that's how that works, right? So let's talk about it. System overview. We've got 3 fuel tanks, right? We've got one tank in each wing, and we've got a collector tank in the center of the aircraft. That's going to be kind of the hub where all the fuel from the wing tank comes, right? We've got 2 ways of fueling the plane. We've got either single point or over the wing refueling. We'll talk about the difference in those. The way that fuel moves around the aircraft, right? So we've got 3 main pumps, right? The low pressure fuel pump, the high pressure fuel pump, and the electric boost pump, right? But So that's going to be these guys right here. Those are the three main pumps in the system, but we kind of move fuel around the aircraft using these motor flow lines and the jet pumps. Jet pumps aren't actually pumps; they're just small ventures. And then we've got the fuel indication auto balancing system is handling through the EDM, right? So it's a lot of computer stuff, right? All right, cool. It's the fuel tanks, right? So wing tanks feed the collector tank, right? Especially because we've got this dihedral going on with the wings themselves, right? So wing tanks feed the collector tank right in the center of the aircraft, right? The collector tank is what feeds to the engine. You've got outboard fuel will gravity feed to the inboard part of the wing for pickup, right? And the wing tanks have vents and cross vent lines, so they'll prevent a vacuum in either of the tank, right? That's pretty cool to know. So if the motive flow and the complex parts of the system don't work right, we're just like gravity feeding is the main way that this is going to happen, right? The motive flow assists the gravity feed, but if you lose it, you're still going to be able to gravity feed from the wing tanks to the collector tank, and that's going to get picked up and sent to the engine. All right, so here's our fueling methods. Single point refueling, right? So single point refueling, over here, here's the little fuel bay on the aircraft itself, right? So the fuel bay there is going to be where they hook up a hose. It's just a big hose, and they're going to pump fuel into the actual aircraft. And like the pressurized fuel coming from a truck is going to go into the tanks and fill up the collector tank, and then it's going to go to fill up the two wing tanks, right? So when we do single point refueling, we're going to get about 1,100 pounds total, right? That's 1,100 pounds max total, right? With single point refueling. Most of the time, you get kind of cheated of that. You're gonna see about 1050, 1060 pounds usually is what you're gonna get when they do single point refueling. Um, on the low end, sometimes you kind of get lowballed and get like 10, 20, something like that. So that's normally what you can kind of expect. 1,100 pounds is going to be max for single point refueling. But the way that breaks down is 530 pounds per wing and then 40 pounds in the collector tank. So math for Marines, 530 plus 530 plus 40 equals 1,100. Over the wing refueling, we can add an extra 100 pounds to the aircraft, right? So over the wing refueling, you've got fuel caps on either wing. You can add 50 pounds to each side, bringing our totals up to 1,200 pounds total, which is 580 pounds in each wing and then 40 pounds in the collector tank. So that is your fueling methods there, right? You're not typically going to see over the wing refueling unless you're doing a really, really long leg on like a long cross country or something like that. And it has to be something the instructor usually has to request ahead of time because it's a little bit more of a pain in the ass to get extra 100 pounds of fuel in there. Um, that all being said, though, like typically, if you need an extra 100 pounds of gas just to be confident that you can make it to the airport that you're trying to make it to for a cross country, maybe do some better pre-flight planning so that you don't have to depend on that extra 100 pounds to get where you're going. Anyway, that's just, I don't know, common sense. Fuel types. We've got a bunch of different fuel types for the aircraft, right? This thing can burn all of this stuff: JP4, JP5, JP8, Jet A, Jet A1, and Jet B, right? All these are acceptable jet fuels for the aircraft, right? Now, the way that this, most of the time, we're just burning Jet A, regular old Jet A that you're going to get at any airport, right? Um, that Jet A does have to contain a fuel system icing inhibitor, right? And then a fungicide, right? So we don't get fungus or anything inside of our tanks, right? That usually comes standard with all like the jet, like anything that we've got contract fuel with, right? Now, uh, you've got the like standard like military fuel, so JP4, JP5, and JP8, right? So I think what the Air Force mostly uses JP8, and the Navy uses JP5, and I don't know who uses JP4, but anyway, they're just it depends on the flashpoints or whatever for the actual fuels there. But most of the time, you're just going to get regular old Jet A. All right, so the way that we do that and the way that we know who can provide us fuel so airport fuel can be found in the IFR supplement, right? This is going to be one of those DoD pubs that's going to be in your publications thing. You're gonna pay more attention to this when you get into instruments, right? But when you start going to outlying fields and doing outings and stuff and doing cross countries, you're always going to check the IFR supplement to see if that airfield has contract fuel with the military, right? If they have contract fuel with the military, then we can throw our government credit card down there and say, fill her up. And they'll fill it up with the appropriate fuel. It's going to be one of these types of fuel, mostly Jet A, and it will be compliant with what we need it to be. So that is how that's going to work for you, right? If you want to go to a certain airport and they don't have contract fuel for us, then tough luck, we're not going to go there. Or you can go there, but you're not going to be able to get fuel there because you can only get the ones from the contract fuel, right? Because that's how it's already been pre-approved and we go up there. All right, cool. Fuel feed to the engine. So this is how this is going to work. So we get fuel in our wing tanks, right? The wing tanks are going to gravity feed down to the collector tank down here. The collector tank is going to be, it holds 40 pounds of fuel, right? So not a whole lot of fuel in there. And that is going to send that fuel up into the, all right, so it's powered by the motor flow line. We're going to talk about motor flow in a little bit. Don't worry about it right now. But the primary jet pump here is what's going to be sending fuel up the main line, right? So primary jet pump picks up the fuel, and it's going to send it up the line to the manifold valve. Manifold valve is basically just kind of a Y pipe where it gets fuel directed from either primary jet pump or the electric goose pump, right? Electric goose pump, you've got that switch inside your plane. You can turn it on. Electric goose pump is just going to kind of be a backup and boost the power or boost the fuel coming into the main fuel line up here. All right, so primary jet pump sucks up the fuel. Kind of cool. It's got the flip-flop valve, right? Basically, it's just a little like the pickup for the pump is on a hose, and that hose is going to flip and flop based on if you're upside down or not, right? So if you're it's going to sit on the bottom of the tank and pick up fuel there until you go upside down. Then it's going to flop to the top of the tank and pick up fuel at the top of the tank, right? This says 15 seconds inverted flight, right? This is outdated. It's 60 seconds inverted flight now. It used to be only 15 seconds max inverted flight, but now it's 60 seconds. So ignore that little part right there. But yeah, that's how that flip-flop valve works. And it's going to provide fuel to the primary jet pump. That's going to send fuel up to the manifold valve, which is going to send it up to the main fuel line, right? Here's the electric boost pump. Electric boost pump, again, right here, serves as the backup to the engine-driven low-pressure fuel pump, right? Remember, the only three actual pumps in this plane are the low-pressure pump, the high-pressure pump, and the boost pump. We'll talk about the jet pumps momentarily and how they actually work. A boost pump caution or a boost pump advisory illuminates anytime the actual electric boost pump is activated, right? So it's going to let you know when the boost pump is on. When you've got the boost pump switch itself has got two positions. It's got on or it's got arm, right? If it's on, it's continually on, right? Most of the time, you're going to fly around with the arm position. In arm, it's going to come on three different instances. It's going to come on whenever the starter is activated, right? So basically, whenever you're starting the plane, the boost pump switch is going to come on. Whenever the low pressure switch comes on, right, meaning that the low pressure fuel pump is not working the way it's supposed to, then we're going to kick on that electric boost pump that's going to back up that low pressure fuel pump. And then whenever you pull your PCL to idle, the PMU is automatically going to turn on that electric boost pump just in case, just pulling it to idle so that we get a little bit extra fuel going up there anyway, so we don't like stall out the plane or whatever. Cool. Fuel feed to the engine. So coming out of the manifold valve, we're going to go to the main fuel line, right? So that main fuel line is going to first come through the maintenance shutoff valve. Maintenance shutoff valve itself, what it does, it's in the fuel bay, right? So like I showed you, it's like right here before you get to the fuel filter. It's a red handle, and all it does is when maintenance needs to work on the engine, they can just shut off the fuel right there without having to pull like a firewall shut off handle or something. They can just shut it off there. Whenever I check this on a pre-flight, I want to make sure that that maintenance fuel shut off handle, it's like a little square or a rectangle. So the rectangle has to be parallel to the deck, right? If it is straight up and down, like perpendicular to the deck, then that means it is cut off, right? You're blocking fuel from going into the engine, right? But so that's what you're going to check on a pre-flight. Little red handle, make sure that's parallel to the deck so it's not blocking fuel. Then we're going to go to the fuel filter. Fuel filters filter until they bypass, right? Because dirty fuel is better than no fuel. There is only one way to tell if the fuel filter is being bypassed. It's a little fuel filter bypass indicator. It's this little red pin that pops out. You can only check it whenever you're looking at the actual fuel filter itself. If it's like just above the fuel filter, this pin pops out and lets you know, like, hey, I am being bypassed and not or I'm not filtering your fuel right now. You'll check it before and after your flight just to see if it's bypassing, right? But if you see it before you go fly, you're not going to go fly, or you're going to get a new fuel filter on the plane before you go fly. All right, cool. Next thing we're going to go to is the firewall shutoff valve, right? Remember, this is connected to our firewall shutoff handle inside the cockpit. That thing is going to be, remember, it cuts off three fluids going forward and after firewall. We've got fuel, that's one of them. And then we talked about hydraulic fluid. And the last thing is going to be bleed air coming forward and aft, right? So we're talking about that with the ECS system tomorrow. But there's your firewall shutoff valve connected to your firewall shutoff handle inside the cockpit. Then we're going to go to the actual firewall, right? And that's what's going to prevent fire from coming into the cockpit itself back there. Nope, going down. All right, cool. Next thing we're gonna do after we go from the firewall, we're gonna come up here. I can't do it because this little thing is gonna pop in the way. We're gonna come up to the engine-driven low-pressure fuel pump, right? So that engine-driven low-pressure fuel pump. Remember, that's gonna be the important one, or not the important one. Uh, it's just the next step in the series, right? And that engine-driven low-pressure fuel pump is going to step up that fuel pressure before it delivers it to the high-pressure fuel pump. So the high-pressure fuel pump doesn't have to suck it all the way from the engine, right? So it increases that fuel pressure in line before it comes to the high-pressure fuel pump. The engine can operate without the low-pressure fuel pump, so it's not as important as the high-pressure one. High-pressure one we must have in order for it to work, right? And remember, I talked about it, shares a common shaft in the accessory compartment with the external oil scavenge pump, right? So remember, if we've got a problem with the oil pump, we've got a problem. We're most likely going to have a problem with the fuel pump as well, right? Or vice versa. Uh, if you got a problem with fuel, you can assume you've got a problem with oil as well. All right, cool. Engine-driven high-pressure fuel pump, right? So this is the one that we must have in order to operate. If we lose the engine-driven high-pressure fuel pump, we're turning into a glider, and we have to uh, be force landed somewhere, right? So that thing is super dependent, right? But we've got all these redundancies that's going to be helping it out, and it's a very robust, overbuilt part, right? Remember, it's going to increase that fuel pressure in the fuel line to it's going to send to the fuel management unit, which is the next step on the line, right? The engine will not operate without the high-pressure fuel pump, and then operating using only the high pressure fuel pump without the boost pump or the low pressure pump is limited to 10 hours, right? And that's again over the lifetime of the part. We're going to keep track of that in our uh, aircraft discrepancy binder. So that is that guy right there. Super important to be had. The next thing that happens in line is the fuel is going to feed to the engine. It's going to go to the FMU, which is the fuel management unit. Basically, this thing is going to meter how much fuel is going into the actual engine. It's going to receive an input from the PCL via a cable or via the PMU, right? So again, redundancies, right? The PCL, you're going to move your left hand and you're going to say like, hey, I want this, I want to go this fast, right? You're telling the PMU out you want to go this fast. The PMU is going to send an electric signal to the FMU, the fuel management unit. It's going to say, hey, he wants to go this fast. He needs this much fuel. All right, cool. We're going to do that, right? If the PMU is shut off, right, then we are going to talk directly to the FMU via a cable, right? Just like just a metal cable that is directly controlling how much fuel you're metering. Again, it's not going to be linear, right? So this is part of how that graph in that last brief that we talked about, right? That nonlinear graph of the PMU off, right, is going to give our power responses, right? It's because we're not being computer controlled. We're literally controlling this thing via a cable, kind of like an old car, right, or a dirt bike or something, right? That's how that's going to work for your FMU. All right, and that's what the FMU is just going to tell how much fuel needs to go into the fuel manifold, right? After the FMU, we're going to get through a fuel flow transmitter, right? Fuel flow transmitter is just going to sense how much, like it's just going to detect your fuel flow, right? How much fuel is coming in the line, and it's going to display it on your ICAS display down here in pounds per hour, right? Um, Typically, so let's say typically you're going to be like um, 500 pounds per hour is like a normal day. So 500 pounds per hour, 1100 pounds of fuel. That's like, yeah, we're gonna get about two hours worth of flying, right? Especially when you're low and you're like fast and like max power or something, right? You could see it go higher than that, like into 500, 600. But remember, you got your max fuel flow, which is this is a new limit I forgot. Let's look at it real fast. Max fuel flow is going to be 799. So down here, 799 pounds per hour. So you never want to see it any higher than that. But like I said, kind of an average is about 500 when you're flying locally, right? Once you get into like going cross countries and are flying instruments and stuff, and you get high up into that nice thin air up there, you can see it drop down here to 166 pounds per hour or something like that, where it's nice and low, and you're getting pretty good fuel mileage for this aircraft. All right, cool. Um, Fuel feed to the engine, right? So now we got the next thing we're going to is the fuel manifold, right? So fuel manifold is what's going to be sending the fuel into the actual combustion section of the engine itself, right? So it's kind of where we collect our fuel, receive fuel, and then it distributes it to all the different fuel nozzles that are going into the combustion section, right? The fuel nozzles, and that's what delivered in there, and that's what's going to spray it into the sprayed in there to get the like fuel injectors for the aircraft, right? There are 21 different nozzles in the aircraft, right? So 21 fuel nozzles on the plane. Now, when you first start up your engine, right, you're going to see two different spikes, right? So when you're looking at your ITT and you're watching your engine start, you're going to see your ITT come up to a number, then it's going to cool down for a little bit, and then it's going to come up to a higher number, and then it's going to cool down for a little bit. That is directly because of the fuel nozzles. At first, only 14 of them turn on, right? So we've got the two different spray patterns. For start fuel, the first 14 come on and they're spraying a little mist in there, and that's what's going to be like getting us ready to start the plane. Once we have light off, right, we're going to see that fuel, like that ITT spike up, and then once that fuel kind of burns off, it's going to cool down for just a little bit, and then we're going to turn on all 21 into a stream, right? And so we've got stream of fuel just coming into the combustion section, and that's what we're going to see it go higher. So you're going to get two peaks on your ITT whenever you're starting the plane. It's something you don't want to be looking out for, because you're going to be responsible for like saying, all right, cool. Like when you start your engine, max ITT was whatever you saw, right? And you want to make sure you bite off in the first peak and not the second peak. That's worth knowing. 21 fuel nozzles total. First 14 come on with start fuel, and then all 21 for stream fuel. Now, let's go back here real fast. Everything that we just talked about, right? We've got from the tanks, right? We went down to the collector tank. We got picked up by the primary jet pump or the boost pump into the little Y pipe that is the manifold valve, sent up through the shutoff valves and filters and firewall. We get increased in pressure for the engine-driven pump, increased in pressure more for the engine, the low pressure pump than the high pressure pump, and then the FMU is going to meter how much fuel needs to go into the engine. That gets talked to by either the PCL or the PMU. And then we go to the fuel flow transmitter, and then we go to the actual engine itself. So that is the simple part of the system. Now, what we're going to talk about next is mode of flow, right? The mode of flow line is actually it's genius, right? So we're taking advantage of physics in order to let this system kind of circulate fuel by itself, right? That's the best way I can kind of intro this, right? But the mode of flow line, right, is going to get tapped off here right between the engine-driven low pressure pump and the engine-driven high pressure pump, right? So we've got almost not a lot of pressure here, right? But once we get to the engine-driven high low pressure pump, we're going to increase that pressure, right? What we're going to do is we're going to tap some of that higher pressure fuel. So this pressure is at a higher fuel. Sorry, this fuel is at a higher pressure than anything down here, right? We're gonna take that high pressure fuel, we're gonna send it in a line. That line is gonna go to circle around the wing tanks, and it's gonna circle around so goes the wing tanks and it goes to the collector tank, right? So the way that this works, so it taps off then there, it goes to it's gonna drive our jet pumps, right? So we've got the transfer jet pumps in the wings, we've got the primary jet pump in the collector tank, right? I'm not gonna talk about that just yet. Let's talk about the way a jet pump works. So the way that all of these jet pumps work is they are essentially little venturis. Okay, a venturi, all it does is what we're going to do is we've got a certain cross-sectional area here, right, at the beginning and the end. And then it's going to neck down to something very narrow in the middle, right? And what that is going to do, so we've got starting out, we've got high pressure and then low velocity of fuel, right? So high pressure coming out of the fuel pump up here. Then we're going to neck that down just like you're putting your thumb over the top of a water hose, right? That's going to be decreasing the cross-sectional area, and it's going to drop the pressure. So the pressure is going to decrease as the velocity increases. So again, just like a water hose, right? You're going to decrease that area, lower pressure, but you're going to get a lot faster water coming out of that, right? So that fuel is going to increase in velocity, right, until it comes back over here where it goes back to the normal size, and we've got higher pressure and then low velocity again. Okay, so that's how all of these jet pumps work essentially, right? What we're going to do is we're going to take advantage of this low pressure zone in the center here, right? So this is low pressure, which is at a pressure that is lower than the pressure in the tanks. That's kind of neat, because what we're going to do is, things want to go just like lift, right? Things want to go from high pressure to low pressure, right? So we're going to suck in fuel from the wing tanks, right? And that's going to push the fuel along in front of it, right? So that's going to join this all the other fuel in the mode of flow lines, right? It's kind of pushing it along. Um, Basically what this does is it creates a circulation of fuel going around the engine, right? Or going around the aircraft, right? So this is constantly circulating, right? And there are no moving parts in here except for the low pressure fuel pump, which is driving all of this. The low pressure fuel pump is what creates that pressure differential. And then we take advantage of physics in the jet transfer pumps and the primary jet pump. All these pumps are the exact same. No moving parts, but they take advantage of physics to circulate fuel from the wings to the collector tank, and then from the collector tank, and that's what's gonna, again, it kind of makes its own little circle with the high pressure fuel pump up there. So its own little circulation there that sends primary jet pump is gonna always be sucking up fuel and sending it up to the engine-driven low pressure fuel pump. So we're just taking a small amount of fuel to create this circulation going around the aircraft, right? I think that's pretty neat. If that went over your head, don't worry about it too much. It does make the system a little bit more complicated, but you will need to be able to explain this when you brief it to your instructor. Now, the way that this works, right, if you don't know anything, right, so this is all based on Bernoulli's principle, right? So Bernoulli's principle, remember, it's the same principle that's creating our lift, right, as well. So if you can throw out Bernoulli's principle, right, and just say the motor flow system works based on Bernoulli's principle, cool. And then if you say that all of the jet pumps are little Venturis that use Bernoulli's principle to create motor flow, your instructor is going to buy that. That's how this works, okay? So if you say Bernoulli and Venturi anytime you're explaining this, all right, cool, you're going to be able to explain it fine. That's how this works technically, though. I like getting technical with this stuff. It's uh, I don't know, probably a good thing or a bad thing. Who knows? All right, so that's the motor flow line there. Now, notice in the motor flow line here, right, after we've come off from the engine-driven high pressure fuel pump, we've got this little guy. This guy is our low pressure switch. Low pressure switch is going to sense when there's less than 10 psi in the motor flow line. There's less than 10 psi in the motor flow line. The thing that is creating that pressure is probably not working, right? What is the thing creating that pressure? It's going to be the engine-driven low pressure fuel pump, right? So you get if this happens, since it's less than 10 psi here, it's going to basically mean that the engine-driven low-pressure fuel pump is not working. The engine-driven low-pressure fuel pump isn't working, then we can assume that we have a problem. Or wait, we're going to get that low-pressure. Sorry, engine low-pressure fuel pump isn't working. We're going to get a low fuel pressure warning, right? Low fuel pressure warning. Remember, this is what's going to give us our EP, right? The critical action item. So PEL execute, then boost pump switch on, because we think that if there's a problem with the low pressure guy, low pressure fuel pump, there's probably a problem with the external oil scavenge pump. Kind of beating that dead horse, right? All right, so that's what gives us this EP though. Neat thing is whenever we get that low pressure fuel pump, right? Remember that's going to be one of the triggers that automatically turns on the boost pump, right? So we're going to get that boost pump that's working there as well. It comes on to assist the high pressure fuel pump, right? All right, so now again talking about the EP the way that it's written. So if so PEL execute first, and then while you're PELing, you're gonna turn that boost pump switch on, so the boost pump is continually on. Otherwise, what's gonna happen is it's gonna cycle on and off, right? The low pressure fuel pump isn't working, right? Trips the low pressure switch. Low pressure switch is going to trip the engine driven the boost pump, right? Boost pump is going to come on, increase the pressure. Pressure is going to get greater than 10 psi. It's going to turn this thing off, right? Which is going to turn off the boost pump switch, right? Which is going to then drop the pressure, and then we're going to hit the fuel pump or the pressure switch, and that's going to turn on. So it's going to cycle on and off as it constantly goes above and below 10 psi until you reach over, hit that boost pump switch on, and then it'll be continuously on, and then it'll stop worrying about it, right? If you don't do that, then you'll constantly get that little thing flipping on and off for you. That's low pressure switch. All right, transfer valves. So first thing I want to point out here, right? So we've got transfer valves here, and then we've got the vent line. Fuel does not transfer between tanks in this aircraft. It's one of those things you see in movies, but it doesn't actually happen here, right? Basically, the transfer valves, what they are going to do, so the vent line, all it does is prevent a vacuum from building up. No fuel actually goes through there. It just keeps the tanks at equilibrium. But the transfer valves themselves here are going to open and close, basically turning off and turning on that mode of flow, right? We're going to use these guys to help balance our fuel, right? The mode of flow, again, it's going to deliver fuel from the wing tanks to the collector tank. Now, that's the way that it's typically going to work. But if we didn't have mode of flow, we're still going to gravity feed, right? So gravity feed is still kind of like the primary way that fuel moves around here. Now, because of the pressure differentials and stuff like that, mode of flow is stronger than gravity feeding. So if we turn off the mode of flow to one tank. So we turn off, say we close this transfer valve right here. We're going to turn off the mode of flow there. Then we are primarily going to be feeding from the left tank, right? Because the mode of flow is going to outpace the gravity feeding coming from the right tank, right? So that's how this works. So if we needed to balance our fuel, we would use our fuel balancing switches. We've got the ability to do that, and those directly control your transfer pumps, right, or transfer valves. Now, the way that this works, right? Let me show you on the thingy here. So we've got our fuel balance switches up here, right? So we've got our fuel balance switch. It's got two positions. It's got manual reset and it's got auto. Most of the time, you're going to fly around it with in automatic. Like that's going to be automatically balancing your fuel and keeping them within limits. It's the computers are doing that. We'll talk about that in just a second, right? Most of the time, that's going to happen. But if we needed manually to manually do it, we'd flip the switch to manual, and then we go over here, and this switch would become active, right? This switch is our manual fuel balance switch, right? It's got three positions. It's got off, which means that both transfer valves are open. If it's got left and it's got right, right? If I switch it to, so if I switch it to either left or right, that is going to close that transfer valve, right? When it closes that transfer valve like that, I'm going to be blocking the fuel from coming from whatever side I've gone it to. So if I go manual fuel balance switch to the right, then I'm going to turn off this transfer valve, essentially blocking the fuel from the right side and then only taking fuel from the left side. So that's kind of the thing. If you ever find yourself out of the limits and you have to manually balance your fuel, right, you're going to switch to the low tank, okay? Block the fuel from that tank, draw from the higher tank, and that's going to bring things back down to the within limits. Once the higher tank joins the lower tank, then we are going to go back to off and back to auto, and then that's going to allow them to continually go down equally, right? That's a common misconception, right? Because think about your Cessna, right? So when you were flying the Cessna or the Piper or whatever, right? You switched to the tank you wanted to draw from, right? So it's opposite of that, right? So in the Cessna, you'd switch to the right tank and you're only drawing from the right tank. Here, if you push the little thing to the right tank, then you are blocking the fuel from the right tank and only drawing from the left tank. That makes sense. I hope it does. Cool. That's how the transfer valves work. We already talked about the jet transfer pumps, right? Cool little Venturis. I like these guys. All right. Fuel indicating system, right? So the fuel indicating system, we have 7 fuel probes in this aircraft, right? All those 7 fuel probes, we're going to send that information to the engine data manager, which is going to send that information to your ICAS display, right? 7 fuel probes, right? So we've got 3 in each tank and then 1 in the collector tank, right? These guys, so there's outer, middle, and inner probe, right? The outer probe, again, they're just kind of spaced out evenly along your tank, right? So the outer probe is going to measure down to 445 pounds plus or minus 50. The middle fuel probe is going to measure down to 308 plus or minus 50. And the inner fuel probe is going to read down to the last 20 pounds, right? Remember, 20 pounds from each tank is going to add up to the 40 pounds in the collector tank. So that's going to be the last little bit of fuel in the wing tanks, and then it's going to be the last 40 pounds. So 20 plus 20 makes 40 in the collector tank, right? Now, the way these guys work are kind of like these are float type probes. Talk about it. Yeah. These are float type probes. So it's like a little float on a stick. And as that fuel goes from high to low, then that fuel level decreases. That stick is going to drop down. That little float is going to drop down, and until it gets to the lower range of that specific probe, and that's going to be picked up by the higher range of the next probe. Okay, so that's kind of how these guys work. So it works kind of like a baton race, right? So one hands off to the other, so that you get seamless reporting of your fuel in your on your ICAS display, right? So they are float type probes, and that is how they work, right? And then we've got the outer one hands off to the middle one hands off to the inner probe, right? Whenever it gets to the of its yes, that is that. Now, actually, for fuel probe failure for this guy, right? You will get a fuel probe failure that will illuminate if you lose one of these probes, right? What it does is it automatically turns off the auto balancing system, so it's not going to auto balancing anymore because it doesn't know how much fuel is in there, right? So if we're up here, say you've got mostly fuel tank up here, right? Then you're measuring with the outer probes, right? Well, if the outer probe on the other side fails, then it's going to drop down. It's just going to read the max of what the middle probe is going to be reading, right? So that's how this guy kind of works, right? So it will read the max, the next lowest one, right? If say your middle probe fails, right? So if I'm both reading, the outer probes are still working, right? Then we drop down, drop down. All right, cool. We're out of the outer probe range and the middle probe has failed. Then we're going to drop, one of them is going to drop straight down to the max of the inner probe. And then the other one is going to still be reading the same. The aircraft kind of freaks out, doesn't know what to believe because it's getting mixed signals from its so from that. So it's not going to try and fuel balance it's not going to automatically fuel balance with one of the probes failed. That way, it doesn't intentionally give you a messed up fuel balance, right? So the auto balancing system fails. Um, so that is how the fuel probes themselves work. They're flow type probes, and they just like a baton race. One hands off to the next when it gets to the bottom end, right? All right. To back up the fuel probes, right? We've got these low fuel or the fuel low level sensors, right? These guys are optical sensors. So it's basically a little eyeball inside your tank, okay? Little eyeball is going to uh, be at the bottom of the tank and it's going to be constantly covered up with fuel until such point that it isn't, right? Or whenever it isn't, it's going to let you know when it becomes uncovered, right? It's going to tell you you've got 110 pounds left in that tank, right? So 110 plus 110 makes 220 plus 40 pounds. So you got 260 pounds left in the aircraft, right? So we're still above our minimum fuel. But it lets you know when you've got that last 110 pounds in the tank when that little eyeball becomes uncovered, right? In which case, it's going to give you a left fuel low or a right fuel low caution message, right? This is kind of a backup. You can have no fuel probes or complete fuel probe failure, right? And these guys will still work because they operate independently, right? So if that little eyeball, that optical sensor comes uncovered, then it's going to let you know by giving you the left fuel low or right fuel low warning. Now, when is a time where I might be kind of low on fuel and coming back in and and making steep turns, right? Whenever I'm coming back into home field and getting ready to hit the brake, right? Whenever you hit the brake, you're going to get a 45, 60-degree angle of bank, and all that fuel is going to slosh from the inside all the way to the outside of the wing, depending on whichever wing is the low down one, and you're going to get a left fuel low or right fuel low down caution, right? Because that fuel is going to uncover that little eyeball inside that tank. Don't freak out, right? Happens all the time, especially if you're coming back in the low fuel state and you do like a more aggressive angle of bank turn. Um, if it happens, that's fine. Fly the airplane, right? As soon as you level back out in the downwind, the fuel is going to come back to cover up this eyeball, and it's going to it'll turn the slide off for you, right? Because the fuel's covering it back up again. Freaks out sometimes. Again, it's just the nature of having liquid fuel in an aircraft, right? Um, but I remember the first time that happened when I was flying the brake and coming into land at home field. I was like, "What the fuck is that? Why am I getting warnings and cautions going off while I'm about to land?" Anyway, that's that. All right, so the fuel quantity indicator. So this is your fuel quantity indicator. It's on your ICAS display. What it does is it's going to show you the total from each. It shows you how much is in each tank, and then it totalizes it down here at the bottom. This is how you're going to tell if the tanks are within balance, right? You're constantly going to be checking to make sure that your aircrafts are in balance, right? If you get all the way down here to below 150 pounds, the whole thing turns yellow, right? The fuel bar down here, like everything turns yellow. This thing turns yellow. And then if you're below 150 pounds, so that's like 300 pounds total, then yeah, you're not going to be able to do aerobatics with less than 300 pounds, right? We're coming into land at that point. All right, cool. Bingo fuel. So now we've got audible like dude that's going to let you know whenever you are low on fuel or whenever you've reached a particular fuel state, right? So we've got bingo fuel. Bingo fuel stands for I learned this is an acronym like last year, is like stands for below if not go on, right? Someone told me that. I don't know if it's true or not, but that's what bingo fuel means. Basically, whenever you reach bingo fuel, it's time to go home, right? We have enough fuel to make it from wherever we are to make it back home and land and still land with our minimums, right? So usually, so like we're coming from the MOA, right? We had set 400 pounds as our bingo fuel. So when we hit 400 pounds or from Goliad or whatever, then it's like, all right, cool. We've got the 200 pounds it takes to fly back to home field and still land with our 200 pounds, right? Which is going to be our minimum fuel. When you do that, you can set this on the upfront control panel, and it's going to allow you to pick any number between 0 and 1200 because that's how many pounds of fuel you've got, and it will give you an alarm whenever you want that. So if I say, "Hey, let me know when I get to 400 pounds," right? You hit 400 pounds, the aircraft will say bingo, bingo, bingo inside your helmet, so it'll let you know, right? We kind of use bingo fuel as everything, right? But we call it different things. We've got bingo fuel and we've got joker fuel. The aircraft doesn't know the difference between bingo and joker, right? But joker fuel basically means it's time to go from high work to low work, and then bingo says it's time to go home, right? The aircraft will say bingo for both of them, right? Still, that's how you kind of set that little. It's just a little fuel alarm. Let me know whenever I get to this fuel state. All right, the fuel balancing system. We are almost done. Yeah, we're almost done here. All right, fuel balancing system. So the aircraft is going to automatically keep our fuel balanced, right? What it does, it keeps the fuel level within 20 pounds of each other, right? And the way that it does that, it's going to again automatically open and close those transfer valves so that we are keeping those tanks balanced, right? Ideally, it should be drawing from one tank to the other, but say like when you get to forms, there's this part of forms where you have to like just sit in this constant 30-degree angle of bank turn for a little bit, or whenever you're in like holding or something in instruments, the aircraft kind of has to do more work by drawing more fuel from one tank to the other to keep them within 20 pounds, right? The maximum lateral imbalance that you can really get is 50 pounds, right? That's the, or well, not that's not the maximum possible, but that's the max that this system will allow, right? If it gets more than 50 pounds, then it's going to automatically shut off and be like, hey, I don't know what's going on. I can't do this. You handle it. It's going to give you a fuel balance warning, let you know that the auto fuel balance shut off, right? Um, but if you get the an imbalance of greater than 20 pounds for more than 30 seconds, right? So it's going to keep within 20 pounds. But if you get it greater than 20 pounds for more than 30 seconds, that's when the auto balance is going to be happening, right? So it's going to start turning things on and off to do that, right? Um, it will try and keep it there. It kind of gives it a 2 minutes to do that. But if a fuel imbalance is not reduced less than 30 pounds within 2 minutes, the auto balancing system will shut off, right? So the two reasons it will shut off, right, is if it's greater than 50 pounds or if it's does not get down to less than 30 pounds within 2 minutes. That means that it's not doing something right and it doesn't trust itself, so it's going to shut itself off and allow you to manually control it, right? You can either hit that fuel balance switch to reset, so again, you go to manual reset and then back to auto, and that's going to reset it and give you another 2 minutes to allow this thing uh, to settle itself out. Or if you just go to manual, then it will power on the fuel balance switch, and again, you can take control of that fuel balance switch by switching to the lower tank, right? Or yeah, you switch to the low tank and draw from the high tank. That's how that works. All right, cool. And that's how the controls work here, right? So you got the fuel balance switch, you got auto or manual reset. It would reset the automatic system by going to reset and back, or just manual, and manual would turn on that manual fuel balance switch. If you go to manual fuel balance, you will get an M fuel balance caution letting you know that you are controlling the manual fuel or the fuel balance of the aircraft, not the automatic, right? Until you go back to an automatic setting, and then it will take care of that. And then again, we've already talked about this switch down here. Whew, that is everything on the aircraft for the fuel system, right? I know it was a lot to talk about. There's a lot that goes into it, right? It's a pretty simple system overall, right? And it kind of happens without you thinking about it. But there is with the fuel probes and the optical sensor and then the automatic balancing system, that all it gets adds complexity to the system, especially with the motive flow. But when you break it down and think about it pretty simply, it's just moving liquid from a tank up to the engine, right? And that's all it's really doing. That is the fuel system. We've got one last system to talk about, which is going to be the electrical system. Again, I'm going to grab some water real fast, and we're going to talk about the electrical system and get ready for that. And that's the last thing we got to talk about. I know today is the long day. Tomorrow gets to be about the same as well, but these are the longest 2 days of 22. I will be right back after I grab some water. One second. All right, let's do it, guys. One last brief. I'm ready. I hope you are too. Ah, almost knocked my computer off. Good. All right, cool. Uh, electrical system. This one goes kind of fast. I like the electrical system. It's actually my favorite system to teach. Kind of weird when you do this so long. You've got favorite systems. Whatever. All right, electrical system. It's okay. Thank you, Google. Bam. All right, so the EP of the day, we're not going to cover today. We're going to cover it tomorrow because with battery bus and operative, we haven't even talked about what a battery bus is. So it's easier to just talk about both of the EPs that relate to the electrical system tomorrow instead of today. But we're gonna bypass that for now. But if I tell you that we have a 24-volt battery in this aircraft, how many volts do you think the generator needs to supply minimum to charge the battery? Well, to charge a 24-volt battery, we need 25 volts to be produced by the generator. We're going to talk about that here in just a second. And the minimum battery voltage. So this is the voltage you get inside the aircraft. You turn on the switch and you look at your voltage, and it's like below this number, you're not going to go flying. That's going to be 22 volts, right? So 22 volts is the minimum battery voltage. You are also going to hear it worded as the it's not just the minimum battery voltage, but it is the do not connect external power below 22 volts as well. So that is both of those. Objectives, we're going to talk about the electrical system and all of its components, right? All right, so here's the system overview. So now, looking at the system overall, looks kind of complicated, little scattered out there, right? But for the most part, it's a brutally, it's not as simple as a fuel system, a little complicated, but it is very redundant in nature, right? So that's kind of where it makes up in things. This is a very robust system, right? You're going to have um, a lot of redundancies in here that are going to help you out, right? Especially because when we start losing electrical components, how does the system operate and how does it continue to provide power to things that we need it to do? So it is mainly a DC system, right? So direct current means that we're operating off of a generator instead of an alternator, right? Your car has an alternator in it, so it's got alternating current. We've got a generator. We're going to be providing direct current for things, right? Um, the power supplied to the main source of power in this aircraft is going to be the starter generator, right? Which is this guy right here, providing most of the power to power everything on the aircraft, right? We do have our battery, of course, right? That battery is going to be like similar to the battery in your car, right? The only thing you really need the battery for in your car is to start the car, right? So the battery is really here for engine starts, right? Or backup power if we lose our generator. That's what the battery's for. Now, backup to the backup, or backup to the backup is going to be our aux bat over here. So the aux bat is in case we lose our generator and our battery. The aux bat down here is going to be the thing that's going to provide just the bare minimum to get us on the ground, right? When possible, it's kind of our emergency source of power. The way we distribute power in aircraft is through a number of different buses, right? So all of these gray boxes on here, these are our buses. They're not school buses; they are electrical buses. So they are going to be basically think of them as power strips, right? All your different components, so they get charged with a specific amount of power, and then they distribute that power to all the different components that are tied into them, right? Which are all the things out here. Everything that needs power in the aircraft will get its power from a bus, right? We'll talk about what gets power from what buses a little bit later. Now, the way that we want to think about the system, right? So everything on the left side of the plane, right? Left side of the plane over here is going to be the generator or the battery side of the plane, right? Then on the right side of the plane is the generator side of the plane. And literally this holds true for most of it in real life, right? Things on the left are battery side, things on the right are generator side. This is the same with your circuit breakers, right? So circuit breakers on the inside the cockpit are going to be on the left for battery stuff and on the right for generator side. So kind of a way to think about this is as you're sitting in the cockpit, you can remember the word big, B-I-G. So batteries on the left, I sit in the center, and the G's on the right, the generator's on the right. If that helps you remember it, cool. So we've got left and right side of the plane. We've also got forward and aft, right? So we've got things that are redundant forward and aft cockpit, right? So we've got stuff in the front cockpit and stuff that is repeated in the rear cockpit, right? And then we turn our avionics master switch on. We've got forward avionics cockpit stuff and aft avionics cockpit stuff. Now, for the most part, everything is in the front cockpit, right? Everything that needs to matter because this aircraft is designed to be single piloted, right? The stuff in the rear cockpit really just goes to support the rear cockpit. So like the MFDs and the upfront control panel in the rear cockpit. So that is kind of what the rear cockpit is for. Whenever you're handling an EP or something, right? Um, Most of the time the instructor's going to be flying from the rear because that's all he can do. You have all of the circuit breakers and everything in the front cockpit that he doesn't have the ability to affect from the rear. So he can fly the plane and allow you to fight the plane by pulling out the PCL and messing with circuit breakers and switches and stuff, right? So that's kind of how this works in the plane. All right, so let's talk about it. That's the whole system in a little bit bigger of a picture. So let's talk about the source of power. So first thing we're going to start at is the starter generator up here, right? Starter generator is going to be this big cylinder inside the engine compartment right here. So that's your actual starter generator. It looks like this black cylinder back here. Oh, sorry, it looks like this silver cylinder. It's not pointed at like those two buttons. It's this big cylinder in the back, connects to the accessory gearbox, and that is going to be your main source of power for the plane, right? In the actual airplane, it's a big black cylinder, right? The starter generator is essentially just a big it's a big electric motor, and that thing does tend to get hot. It's going to need to be cooled down, right? So we've got our starter generator air intake duct right here. So this little triangular cutout in the plane actually goes to a big black hose. It's going to come up and provide cooling air for the actual starter generator itself right there. It's important. One of the games instructors like to play with you whenever they're pre-flighting the aircraft is they like to play, what is this hole in the plane? And if they point to this hole right here, that triangular one, that is the starter generator air intake duct, and that provides cooling air for the starter generator. Here's what we need to know about the starter generator, right? So it is dual use. It is both a starter and a generator, right? How is that possible, right? Well, it's essentially a big electric motor. The way an electric motor works, right, is it's a coil of copper wires, the big coil of copper wires, right, with a magnet inside of it, right? Now, magnet produces magnetic field, right, just by existing. As that magnetic field, if you were to rotate that magnetic field induces an electric current. It causes the electrons to move inside the coil of copper wires, right? Cool. We can affect that in reverse as well. We can send a magnetic current through that coil of copper wires, which would affect that magnetic field and rotate that magnet. So one way or the other. Typically, when it's being a starter, we're using battery power to send a current through that coil of copper wires. We are turning that magnet. That magnet is connected to the accessory gearbox and thereby connected to the engine. And that's what's going to turn the engine over to get things started, right? It's got a lot of torque. Electric motors are very torquey. So it's going to be able to do that. Once that engine is turning, we get that fire lit, so it doesn't have to be a starter anymore.
Your microphone is off.
All right, now everyone can hear me, right? All right, so I lost connection there for a little bit, and it kicked me out. So we're back to it. Let's go back to the electrical system. Sorry, let's finish this because I'm tired of talking this morning. All right, we're talking about the electrical system, starter generator, providing 28 volts, 300 amp hours, right? Again, it's located in the left side engine compartment, right? That's where we're going to be able to find it, and we get cooled by that air intake duct on the side of the cowling. Over here, the starter generator is controlled by the generator control unit. It's basically the little computer that is inside the plane, just keeps the generator within limits, right? It's located only in the rear cockpit underneath the panel immediately after the O-box regulator. You literally need a screwdriver in order to get to it, but that's where it physically is. And again, it's on the right side of the plane, so it's on the generator side of the plane, and that just keeps everything within limits there. All right, controls and indications, right? For this, we've got our limits up here, right? So our limits, we're always going to be always between 50 and -2 amps, right? So no greater than +50. For greater than +50, that's going to be too much amps. We're going to start popping circuit breakers and frying equipment. If we've got this is excess amps. I know we're producing 300 amps up here. This is amps that are not going to be used for anything, right? So if that gets read out on your ICAS display over here, you'll see how much excess amps you have, and that's typically going to charge the battery, anything left over, right? But if we're greater than +50, that's going to be too much excess amps, and that's where things are going to start frying, right? If we are over here, we're less than -2 amps, right? So if we ever see -2 amps down here in our ICAS display, that is we are using more, or anything less than -2, we're using more power than we are creating. Typically, something is drawing too much power, or it's something's not working. The generator's not working appropriately. We are draining the battery at that point if we're less than -2. For voltage limits, we're always going to see ourselves between 28 and 28.5 volts. So for this one, whenever you do your ops checks and you're checking you're always going to check your amps and your volts when you're looking at, you're doing an ops check. You do this every 15, 20 minutes inside the plane. You're going to see it somewhere between 28 and 28.5, usually 28.2, 28.3, somewhere right in the middle there. You notify maintenance if it's ever outside of it, right? If the generator is ever continuously below 25 volts, that means your battery is degraded, right? And you're going to want to land as soon as practical. For battery charging, right? It's the way the generator charges the battery. So once you get the generator going, right, it's producing power for things, you turn that generator switch on, it goes to power everything on the generator side of the plane. Power comes across the bus tie right here. We're going to talk about him in just a second. And he's going to go north to charge the battery, right? That battery, so charge the battery there, and this will come south to power the battery bus. And the battery bus, in turn, is going to charge the auxiliary battery, right? So we're going to get that's how we're going to charge everything on the plane. The bus tie switch right here, this is the only place in the system where power is going to flow both ways, from the battery side to the generator side and vice versa, okay? So normally when it's in the normal position, that's like having a switch that's closed, right? And the circuit's going to be like closed there, allowing power to flow both ways, right? If you were to open up the bus tie switch, it goes to open, you're like opening the circuit. That is going to sever the connection between both sides, which means the battery is only powering the battery side, and the generator is only powering the generator side, meaning that there is no battery charging, right? So we're going to be kind of limited on power there. I'll talk about that here in a second. Controls and indications, some more of this stuff. So we've got this is on the right side of the plane. This is up at the very top three switches that you've got. You've got gen aux bat switch and your generator reset button, right? The battery and generator switch are kind of important. They are important, but they're unique switches, right? They are magnetic switches, which basically means they can only be on in one cockpit at a time, right? You have both battery and generator switch in the front and rear cockpit, right? To turn things on. The reason it's that magnetic switch being only on in one cockpit at a time is like, say you're flying around solo, right? And you like a seatbelt gets loose or something in the rear cockpit, and it were to flop over on the panel and knock one of these switches on, right? But knocks one of these switches on, and then you have like an emergency of some sort, and you need to turn your battery or your generator off, right? But you don't have control over that switch, then you're not going to be able to do that until you were to come in and land. Or say you're trying to come in and land and shut the plane down at the very end of the day, you need to get in the rear cockpit to do that. So these switches are tied to each other magnetically, which allows them, or kind of electrically and magnetically, which is if I turn the battery switch or the generator switch on in the front cockpit, it will be off in the rear cockpit. If I turn it on in the rear cockpit, it will shut off in the front cockpit, but the generator will stay online. To take control back in the front cockpit, I would just turn my switch back on, and it would turn off in the rear, and the generator stays online. So that's that. Over here, we get the generator reset button. This guy directly controls the GCU, that generator control unit. If ever I have the generator out of limits, then I'm going to press and hold this button for a minimum of a second, try and get my generator back online or back within limits. So that's what that guy's for. All right, here's our battery. Our battery is this big silver box inside the um, engine, the engine compartment up here, left side engine compartment, right? It is a 24 volt, 42 amp hour sealed lead acid battery up here. So 24 volt, 42 amp hours. The way that I remember that is because it's kind of like a mirror. 24 mirrors over to 42. That helps you. I hope it does. But yeah, that's our battery right there. It's again, its main purpose is to provide power for engine starts when we're starting the engine, right? It is capable of powering the entire electrical system with the exception um, of the air conditioning, right? For a total of 30 minutes if the generator fails, right? So remember, it's kind of our backup to our generator, but if it fails, it can power everything except for the AC for 30 minutes. Now, that's a soft 30 minutes, right? That depends on how fast it takes you to shed the generator side of the plane, right? Or sorry, it will power the battery side of the plane for 30 minutes, right? With for up to the battery side of the plane up to 30 minutes when we open up that bus tie switch and shed the generator side of the plane. Depending on how fast we get to that bus tie switch, that will kind of eat into our 30 minutes here. So if you were to lose the generator side, we're going to talk about this with the EP tomorrow, but if you were to lose the generator side, that is going to kind of uh, eat into your time there. All right, it's a soft 30 minutes. Also depends on how many radio calls you're making as well. All right, battery charging. Battery charging is accomplished via external power, right? So we can hook up a start cart to the airplane that would charge up the plane, or the generator itself needs to be supplying at least 25 volts in order to charge that battery there. We talked about that limit a minute ago. Again, controls and indications. So it is a magnetic switch. We just talked about that. It's the same as a generator switch. It can only be on in one cockpit at a time. Anytime you've got positive amps, the battery is always going to be charging. You got your limits down here. Do not connect external power below 22 volts, right? Which is also the minimum battery voltage. You're not going to go fly below 22 volts. And then 23.5 volts is the minimum for an engine start using the battery, right? So if you don't have if you don't have an external start cart, right, or whatever, you cannot start it if you've got less than 23.5 volts on the battery, right? Remember, it's only 24 volt batteries. So it's like half a volt there. The only time this ever came into play for me was we were on a forms flight and I was winging my buddy's lead. And whenever it came time to start the engine, right? So he was troubleshooting. So we got through our checklist. We're like, all right, ready for an engine start. They said, hold up, we've got we're troubleshooting something right now. As they're troubleshooting, I'm just waiting. I'm watching my battery voltage kind of tick down. I'm seeing it go to like 23.9, 23.8, 23.7. Finally, at 23.6, they came up on the radio and said, hey, we're ready to start our engines now. I'm like, thank goodness, because we were about to start our engines without you because we wouldn't have been able to anyway. So that's the only time I've ever seen that come into play in real life, right? And we were on an out and in doing, so we didn't have access to a start cart, or it would have been a pain in the ass to do a start cart. All right, here's our aux bat, right? So the aux bat up here again. Remember, it's a backup to the backup, right? So the backup to the battery, and it's only 24 volts and 5 amp hours, right? It's located in the left side avionics compartment, which is behind the rear cockpit, right? The avionics compartment is behind the rear. It gets its charging through the battery bus, right? So the battery bus needs to have power in order to charge the aux bat, right? Normally, the battery bus is going to power the aux bat bus as well, which is going to have the three things on it the aux bat that has power to, right? So the battery bus normally powers the aux bat bus, but the aux bat will power the aux bat bus in the event that we lose our main battery and our generator. That's how that works. Like the battery is capable of powering the aux bat bus for about 30 minutes of power. That is again a soft 30 minutes, right? Depending on how many radio calls and stuff you're going to be making using that power, right? The things on the aux bat bus, there are three things on here. We've got a backup flight instrument, we've got our COM2, we've got our fire detection loop number 1. Let's take a second and just talk about these real fast. So the backup flight instrument is going to be this guy right here, right? So this is it's like a little mini PFD, right? Whenever we lose our like main battery and stuff, this is what's going to be powered. This is how we're going to fly. It tells you everything that you need to know, right? It's got you got your altitude, your airspeed, your attitude, your altimeter, like your altimeter setting, your VSI, and your heading. All of that in one little thing. So you kind of got to like get close to look at it, especially. I mean, we've all got pilot eyes, right? So that's your BFI. That's where you're primarily going to be flying off when all these screens go dark and you lose those. But that's going to be good. Now, fire detection loop number 1. So we've got 2 fire detection loops. Both these guys snake around the engine. They're just little wires that go around detecting fires anywhere. they're going to light off the fire light here. We've got fire detection loop number 1 and fire detection loop number 2. Again, redundancy's sake because we're in aviation. So that's that. Now, let's talk about radios. So the radio on the aux-bat bus is going to be COM2, right? So we got 2 radios in the aircraft, right? We've got a UHF radio. We're going to control our UHF radio, so the ultra high frequency, up here on the top, top little window here, right? Then our VHF radio, we're going to control him down here. So UHF and VHF, that's where you're going to put in your frequencies. You dial them in, and then you press enter, and you put them in there. So that's how that works. 2 radios, UHF and VHF. UHF, we are going to use to talk to primarily military, right? So military uses UHF, civilian uses VHF. Whenever we're flying around here, we're talking to like civilian controlling agency, particularly like Corpus Approach, we are going to be talking to them on UHF because just of the high volume of military traffic there is around here, they're going to be talking to us on UHF instead of VHF. But when you leave here, go on cross country and go anywhere else out of the local area, then you're gonna be talking to like center and approach and everybody on your VHF radio. So this is gonna be important. We're gonna talk about this a lot more next week as we get into course rules and stuff. But radio management using your UHF and VHF radios appropriately is going to be important whenever you get there. We'll talk about this a lot more next week, so don't fret about it right now. So that is your UHF and your VHF radio, right? We've got our standby VHF control head. Now, whenever power, we're not going to have the upfront control panel, so we're not going to be able to control things up there. Instead, we've got the standby VHF control head over here, which is going to use the same VHF radio. It just gives us a different way to control how we use it, right? So that's going to be this over here. It's going to be on the right side, kind of like right here as you're flying the plane. That's allows you to turn it on. You can dial in your frequencies. You've got your coarse and your fine tune. Like you can put both of those in there once you power it on. That's going to be using the aux-bat to power your VHF radio in the event that you lose everything else, right? This kind of leads to a funny story. When I was in contacts, my instructor asked me, he was like, "Hey, Whedon, so how many radios are inside the cockpit of the aircraft?" Right? And I said, "Sir, there are 2 radios. There's a UHF and a VHF radio, right?" And he said, "That's wrong, right?" And he's like, "Okay, that's kind of weird." I was like, "Does the rear cockpit like have a separate UHF and VHF radio?" He's like, "No, they both use the same UHF and VHF radio." I was like, "Okay, cool." Does the standby VHF control head count as its own radio? I was like, "Nope, it uses the same radio as before." Then I was asking stupid questions. I was like, "Does the transponder count as a radio?" Just whatever, I couldn't figure out the answer. He's like, go talk to maintenance and then and come back and like find out, right? So I went and talked to maintenance. I was like, "Hey, how many radios are inside the aircraft?" It was like, "There's 2. There's only 2 radios that they have to work on. There's a UHF and a VHF, right? Works in the front cockpit, the rear cockpit, or the standby." All right, cool. That's what I thought. So we're getting ready to gear up, and we're done with our brief and everything. We're down in the paraloft, putting all on our gear, and he's like, "Hey, Whedon, did you ever figure out how many radios are inside the cockpit of the aircraft?" And I was like, "Sir, I talked to maintenance. There's 2 radios. There's a UHF and a VHF. I don't know what you're talking about." He said, "There's actually 4." And he's like, "Do you know where the other 2 are?" And again, we're putting on our like vests and stuff at the time. Like, what? I have no idea. And then he's like, "Whedon, what's on your chest right now?" And again, when you're flying and you're wearing all your flight gear and stuff, you've got a survival radio right here. So you've got one right here, and then he's got one on his chest. So that UHF plus VHF plus 2 survival radios makes 4 total radios in the aircraft. And I was like, "All right, you got me." He had me going for like a week on that one. And it was, I don't know, it was annoying. But if you ever get asked that question, there's only 2 radios inside the plane. There's a UHF and a VHF. The front cockpit and rear cockpit use the same radios to talk. And then the standby doesn't count as another radio itself. So that's how you can kind of remember that kind of stuff. Anyway, back to the electrical system. Let's get through this. What time is it? 11:23. We're almost done. All right, so that's the aux-bat. That's kind of all 3 things in the aux-bat bus. Again, the BFI, the COM2, which is your VHF radio or your standby VHF control head, and then your fire detection loop number 1. All right, controls and indications. Aux-bat switch, only in the front cockpit, right? So you don't have to worry about it getting switched onto the back cockpit. It's not a magnetic switch. It's just on or off, right? And it's only in the front. Then you got your system test panel down here, right? So this is, again, we talked about our lamp test switch earlier today. Your system test panel does have an aux-bat. When you're doing your aux-bat test switch, when you're doing your before exterior inspection checklist, right? So before your pre-flight, you're going to be going through and testing a whole bunch of things. One of those things includes testing to see if you've got a good aux pad. What you're going to do is press and hold the switch up for about 5 seconds. If that little green light stays on for more than 5 seconds, then you've got a good aux pad in the aircraft. That's what you're looking for. External power. External power is back here just behind the speed brake. So it's whenever you give the signal to the lineman, he's going to go around the left wing and behind the plane, and he's going to plug it in back here. So that's where you're going to get that aux power coming in. Remember, we do not connect external power in this aircraft below 22 volts on the battery. It connects directly to the battery and then distributes to the 4 battery bus and everything else. Cool thing about it is the aircraft does have internal protection for over and under voltage. So if the start cart's on the fritz or something, it will automatically disconnect from the start cart so that it doesn't fry the plane in any way. All right. So for the buses, so this is how we get power distribution to all the components, right? So you've got your buses here, which are literally just metal bars, right? Metal bars. Again, you can think of them as power strips, right? And all the components that get plugged into the bus are just like plugging into a power strip, right? And that will distribute the charge evenly and give every component the power that it needs to be powered. So that's how the buses work themselves, right? Between the actual bus and the component that it's connected to, everything is going to have a circuit breaker, right? The circuit breakers themselves, all right, so they're all going to get routed to the front cockpit, or they're mostly all going to get routed to the front cockpit. There's a handful that don't make it to the front cockpit. I'll tell you about those in a second. But everything that you've got in the front cockpit is going to be repeated in the rear cockpit as well. But these are the circuit breakers, right? Circuit breakers will pop to disconnect, so they have a number on top of them, right? If they sense that many excess volts going to that component or that many excess amps, they're going to go ahead and pop. So they pop out like this, like a 1/4 inch with a little white color around them. They're super easy to identify when you've got a popped one, right? And that would just kill the power going to that thing, right? So you don't have that component anymore, right? That's how we kind of protect things, right? So you can reset it, right? If you reset it, hopefully it stays down. Otherwise, if it's still getting too much voltage, it'll pop again, right? You never want to press and hold a circuit breaker in, or you will fry that component. With this, we can use circuit breakers to our advantage, right? So sometimes they pop to protect things, right? But kind of like, like turning when you've got a problem with your computer at home, best thing you can do is just turn it off and turn it back on. Well, we've got a whole bunch of computers in this aircraft that sometimes like flake out on us. For instance, the what's it called? The TAD, the trim aid device, right? Trim aid device is a device that was put in this aircraft to kind of compensate for the rudder, or for the P factor in this aircraft. So what it does is it automatically gives you a little bit of rudder trim to compensate for the propeller, because we've got a big ass propeller on this plane, and it wants to, like, it creates a lot of P factor, right? You are still going to have to trim your rudders themselves, but the TAD is going to automatically give you some of that rudder trim and help trim out some of those forces, right, initially. The TAD is kind of a finicky little device, though. It likes to fail a lot, right? I guarantee you every single one of you is going to get a TAD fail at some point while you're flying. Cool, no problem. Best way to fix that is literally reach over. It's on the generator side of the plane. Reach over on that TAD circuit breaker. You can pop it out and then push it back in. Turns off the computer, turns it right back on, and then hopefully it comes back online. So if you get a TAD fail, it's usually the fix for it, right? You can go to the PCL and actually see what the actual procedure is for it, but that's typically what you end up doing. And then if it doesn't come back online, or if it stays failed for some reason, well, we don't need it because we can just trim our rudder normally anyway. So anyway, it's kind of a nice to have there. But that's how we kind of use circuit breakers to our advantage. You can turn things off and turn them back on with them. All right, the only circuit breakers that aren't in the front cockpit are the stuff in the hot battery bus. Hot battery bus is stuff. So it's these circuit breakers inside the engine compartment. This is everything that's determined that needs to always have power in it. It only draws a little bit of power, even when the aircraft is off and sitting out of the line. These things are still drawing just a little bit of power. And we're going to talk about all the things in the hot battery bus here in just a second, right? But they're important accessories, stuff that is always connected to the battery, right? And then if any of these circuit breakers pop, you are not going to be able to reset them, right? Because they're in the engine compartment. All right, we talked about our bus tie switch. Bus tie switch is the only place, or the bus tie itself is the only place where power can go from the generator side to the battery side and vice versa. Opening up that bus tie switch severs the connection between both sides. You will get a bus tie caution whenever this happens, right? And then the generator and battery, like, yeah, they will. The generator will be providing power for the battery for the generator side, and the battery will be providing power for the battery side. We will be time limited because the battery will not be getting charged if the bus tie switch is open. That's that. All right, now we got a whole bunch of buses, right? So we got the 4 battery bus, we got the 4 generator bus, we got the aux bat bus. We already talked about him. We got the aft generator and battery buses. We've got the avionics master switch. We'll talk about him in just a second. Forward and aft avionics battery buses and forward and aft avionics generator buses. All of those things that I just mentioned, those are all the buses, all these gray boxes, right? Let's go through and talk about them, right? So the first thing that we mentioned up here, we're just talking about the hot battery bus. Again, everything that constantly needs power. So like your clock. Clock has to maintain its own internal temperature or internal time in the aircraft, right? So the clock is always going to be there. Your chip detector is always going to be on. Drawing a little bit of a magnet or a little bit of electric charge to power that magnet to get any chips out of your oil, right? Your O-box itself doesn't stay on, but it is controlled via a different switch. You get your actual O-box switch, which means that the engine doesn't have to be on to turn your O-box on, right? Which is like, oh, if we have an engine out at a high altitude, right, cool, we can use battery power to power the O-box to continue breathing if we're up there until we get down below 10,000 feet. Your FDR, that's your flight data recorder. Again, that's the black box. It's actually orange inside the aircraft. It's going to be recording everything that you do, and it's how we the thing that survives the crash to determine how you crash the plane. Your battery switch, because it's a magnetic switch, right? So it keeps that little magnet switch where it's supposed to be. Your ELT, that's your emergency locator transmitter. That's how we find the black box whenever you put the aircraft in the ground. The emergency flaps are redundant to your actual flaps, your flap control over here. Again, redundancies in this aircraft. I'm going to try and point them out as we go through all of this stuff. And then your ram air valve. We're going to talk about him tomorrow with the ECS system. Okay, so that's your hot battery bus. Again, everything that kind of draws a little bit of stuff. Now, whenever you're briefing the electrical system, it's going to be important to know. You don't have to know everything on every bus. It's awesome if you know that. But if you can rattle off a few of the things that are on the bus that you mentioned, so if you can just rattle off like a few of these guys, the important ones at least, that'll satisfy your instructor, right? All right, now we're coming over here through the battery and coming down to the 4 battery bus, right? I like to think of the battery side of the plane as the need to haves, and the generator side of the plane is the nice to haves, right? So the need to haves on the battery side of the plane, we've got basically everything that we need to have to fly and then land and do everything on the plane, right? So you've got IAC number 1. This is your integrated avionics computer, right? This basically runs your bank of MFDs in the front cockpit, right? Runs all your computers. Your instructor has IAC number 2 that runs the rear cockpit, but they can repeat off of each other so that if IAC number 1 fails, then you can use IAC number 2 to run the front cockpit and the rear cockpit, right? That's kind of how this guy works. Now, note that typically when there's redundancies in this plane, they are on both sides of the plane. So IAC number 1 is over here. All right, cool. The redundant component is over here on IAC number 2, so that if I lose my battery side or my generator side, I still have something that's going to get me by. Remember, this is a very redundant system, and it's going to help you get. You're going to have stuff even when you don't have stuff. I've got my upfront control panel and my right-hand MFD for the forward battery bus, or for the front cockpit, and then on the aft battery bus, I've got the upfront control panel and the right-hand MFD for the rear cockpit, right? So that's going to be both of those. Again, there is more stuff on the aft buses. Like the aft buses look pretty vacant here. It's just stuff that are like minor components or stuff not worth really mentioning on here. So I promise you there is stuff on the aft generator bus. It's just minor stuff. Over here, I've got so now I've got everything else that I need to start the plane, right? So makes sense for the 4 battery bus because it's connected to the battery. I don't have a generator going yet because I haven't started the plane. So everything else over here is for starting the plane, right? So I've got my PMU, my power management unit. Again, that's going to kind of govern the start of the aircraft. My engine data manager, that's what's going to spit out everything on my ICAS display. Lets me watch that as I'm starting the plane. I've got my starter, right? So again, the whole starting relay itself has to it needs power because it's going to draw that power from the battery. The boost pump switch, sorry, the electric boost pump itself, remember that comes on whenever we're starting the plane. And I've got the igniters, right? The igniters are just the giant spark plugs in the combustion section of the engine that are going to light your fire whenever it's whenever that fuel is into the combustion section. Over here, I've got stuff that I need to land the plane. So I've got my landing gear control, right? Remember, we just talked about the hydraulic system and that emergency landing gear, or sorry, the landing, all the stuff that we talked about just a second ago with a hydraulic system. Landing gear control has got all that stuff, controls all of our light bulbs, all of our sensors, and everything that senses where our landing gear is. It's the landing gear control, and it controls the actual the selector solenoids that are going to be putting that landing gear down, right? Whenever I put my handle down. So landing gear control is important, and it's on the battery bus because it is an absolutely need to have in order to get that gear down. But if we lose all electrical power to the aircraft, right, we're still going to be able to get our landing gear down via our emergency landing gear handle, right? Even if our landing gear, because it's an electric switch that puts the hydraulic system down. Cool. We've got our flap control. Again, our flap control up here is redundant to our emergency flaps up here. So interesting point about the flaps themselves is if we lose battery power, right, even though they are hydraulically actuated, right, we lose complete battery power on the forward battery bus and the battery itself, which means the hot battery bus loses power, then we are our flaps will automatically retract. They want to retract their default position, which will be up, right? We got our prop system. We talked about our prop system circuit breaker. That's going to power that feather dump solenoid and allow that oil to come out of the pitch change mechanism. And then we've got the aileron, elevator, and rudder trim all on the forward battery bus, right? So we've got that there. Forward battery bus is going to constantly be powering the aux battery bus, which has got our backup flight instrument, our COM2, which is our VHF radio, and our fire detection loop number 1. And then it's also going to power the aux, or to charge the aux bat itself. Remember that 24 volts and 5 amp hours there. All right, cool. That is the need to have side of the plane, right? Let's come over here to the nice to haves, right? So we're going to open up that we're going to make sure that bus tie switch is in the normal position. So we're going to come across, and power is going to power the forward generator bus and the aft generator bus, right? So the forward generator bus, we've got our air conditioning, right? Air conditioning is nice, especially down here in South Texas, right? Despite your instructor thinking that the air conditioning is for them, the air conditioning is really, I mean, it's there to keep you cool, both of y'all cool, but it's really there for the avionics, right? So even if it's winter time outside, you're still going to turn that air conditioning switch on because that's what's going to keep our avionics cool inside the avionics compartment. You've got your trim aid device. That's that finicky thing that I told you about. Keeps the rudder in trim. You've got your speed brake. We've talked about the speed brake. Remember, no speed limit on the speed brake, but definitely get it in before you overspeed the aircraft to 316 knots. Your nose wheel steering gives us that left or right of center line, plus or minus 12 degrees. You've got your engine data manager. Again, your engine data manager is redundant on the generator side and the battery side because it's that important of a thing. You've got your fuel balance, right? Again, it's nice to have that fuel balance, but we can also manually control our fuel balance there. That's that automatically fuel balance there. Fire detection loop number 2, again, redundant fire detection loop number 1 on the aux-bat bus over here. Then we've got our angle of attack, our pitot heat, and our total air temperature probe. All of those things need to be heated so that they don't ice over, right? Cool. Next thing we've got is our avionics master switch down here. Avionics master switch is what's going to turn on all of the avionics buses in the back. Now, important to know, when I turn on the generator switch, I'm going to get power to all of the generator buses, right? Turns on a lot of avionics all at the same time, or a lot of electrical components, right? When I turn on my generator switch, the first thing I'm going to do is I'm going to check my clock. I'm going to say, all right, clock says 10 seconds, turn on the generator switch, right? Well, between turning on the generator switch and turning on the avionics switch, master switch, I'm going to go to the next couple steps in the checklist, right? It's like 4 steps afterwards, and then you get to avionics master switch. 10 seconds need to have passed before I can turn this on. That way, it doesn't overload the electrical system, right? When I turn all of this stuff on at the same time, right? If I were to go straight to generator switch and avionics master switch at the same time, then we would risk some of these components not coming on at the appropriate time. So make sure 10 seconds has passed between turning on the generator switch and turning on the avionics master switch. All right, cool. Clock now says 20 seconds, avionics master switch on, and I get all the forward and aft avionics generator and battery buses, right? On the avionics battery side of the plane, I've got the center MFD for the forward and aft cockpit. It's kind of the most notable thing on that side. And then on the generator side of the plane for the forward avionics, I've got IAC number 2, remember redundant to IAC number 1. I've got my left-hand MFD, right? I've got my air data computer. That is the kind of just interprets your air data and your pitot and static information coming into the plane. I've got my IRS, that's the Internal Revenue Service. They take your money away from you. No, I'm just kidding. It's the inertial reference system, right? Basically uses accelerometers to help the aircraft determine where it is in time and space based on how it's moved. It's a backup to the GPS, essentially. I've got my COM1, right? So COM1 is over here on the on the generator side, where COM2 is on the battery side. So I've still got a way to talk if I lose one side of the aircraft. So there's COM1 over here, my UHF radio. I've got my TCAS, my traffic collision avoidance system. Basically lets you know where anybody who's squawking anything is in relation to you, as long as they're within range, right? That's your TCAS there. You got your radar altimeter. Radar altimeter is going to come on automatically below 2,000 feet AGL and just read out on your PFD and let you know how far you are above the ground. Your distance measuring equipment, that's going to tell you how far away you are from things you want to know how far away you are from. So like when you're in instruments and you need to know how far away you are from an airport or from a VOR or something, your DNA is going to read that out for you. And then you've got your transponder, so whatever your squawk is, it squawks on the generator side, right? And then on the aft avionics battery bus, you've got your left-hand MFD down here as well for the rear cockpit. And that is everything. Woo! Got through all 4 of those briefs today. That's everything that I've got for y'all. Oh, wait, one more thing. Let's talk about the quiz for the oil prop and the Hydes system real fast. All right, I'm just going to go through these questions for you so you got the answers. Systems quizzes. Hydraulic system. Let's start with this guy. Hydraulic system pressurizes 3,000 plus or minus 120 psi. Hydraulic pump needs a minimum of 1,800 psi to operate. The hydraulic reservoir has 5 ports in the hydraulic system, right? A Hyde fluid low caution message illuminates when there's less than 1 quart remaining in the reservoir. A hydraulic fuse, right? Remember, fluid flow limits the emergency system side if it detects a leak greater than 0.25 gallons per minute. The pressure relief valve activates between 3,250 and 3,500 psi. The emergency accumulator holds a helium precharge of 3,000 psi on one side of the accumulator diaphragm. And EHID pressure low caution illuminates at 2,400 plus or minus 150. Remember, halfway in between. Check engine light when hydraulic pressure is less than 1,800, and check engine light when hydraulic pressure is greater than 3,500. All right, last one down here, oil system. Prop maintains a constant system or constant speed of 2,000 RPMs at 100% NP. Prop produces 2,750 pounds of thrust at sea level and 0 airspeed. Low pitch blades are approximately 15 degrees on the perpendicular plane. Feather blades are 86 degrees on the perpendicular plane. Electronically controlled by the PMU, then NP is normally 100%. Prop overspeed is 110% NP. Sustained prop operation on the ground are prohibited between 62 and 80% due to ground resonance. Oil system capacity is 18.5 quarts. The T6 is limited to 60 seconds of inverted flight and 5 seconds of intentional 0G. And maintenance is going to check the engine oil level between 15 and 20 minutes after it's shut down for the most accurate results. Now, the reason we do these quizzes and I put these questions up there is because they are taken straight from the question banks over in Training 4. So you'll be prepared for that's kind of how the questions are whenever you get to the systems quizzes over there. So you've got access to kind of sample size of those questions. That's everything I've got for today. I'm tired of talking. If you have any questions, please stick around, put them on the chat. Otherwise, I'll see you tomorrow morning at 09, and we're going to talk about the ECS, the OBOGs, and we're going to recap the fuel and the electrical systems. So last day of systems kind of tomorrow. But all right, cool. That's all I've got, guys. Thanks a lot for sticking around. Kill.
Hey, this is Lieutenant Weiss. I just want to let you know I've got duty tomorrow, so I'm not going to be able to make it to the
What duty do you have?
GDO.
Oh, dude, just pop me up on your GDO computer downstairs. It's easy.
Oh, sweet. All right, we'll do.
Log into the computer or bring your laptop, whatever you want.
Sweet. All right.
Yep. Stop recording.